of this year, this financial year, where we thought that the most upcoming and most discussed emerging computational technique, which is quantum computing, quantum computation, we should have an introductory workshop on that, and we try to see what are its applications in understanding some of the fundamental molecular structure issues. And we are fortunate to have two eminent people who have been working long on in this area in quantum computations. Our first speaker will be Professor Sonjoy Majumdar. Professor Majumdar has a PhD from Indian Institute of Astrophysics, and then after a few years postdoc in Germany, he joined IIT Madras for a brief duration and then relocated to IIT Kharagpur, and since 2007 he is in IIT Kharagpur. He has been a visiting professor also. He has supervised several PhD students, has a number of publications in international journals of repute, and he's running several research projects. He's a professor in Department of Physics, and he has been head of Center for Theoretical Science. Huh? Okay, we had a Center for Theoretical Sciences. He headed that center also for a duration. And Professor Majumdar's research interest involves quantum optics, quantum computation, and information, and especially his group is looking into quantum programming in recent times. So I leave the stage for Professor Majumdar. Please. Just one minute. For the online participants, I request you to mute your microphone, and if there is a switching to the board, Professor Majumdar will go to the board, and you can, instead of screen, you can look into the board, which is also shared to our camera here. And if you have any question, please raise your hand. After the session, we'll take the questions. Thank you. Please mute your microphone for so that the clarity of sound can be maintained for all.
রেকর্ডিং হচ্ছে, ঠিক আছে। মিউট কেন দেখাচ্ছে না? বলা মিউটেড হবে। ঠিক আছে, আপনি এবার স্ক্রিন শেয়ার এটা
I can minimize this one.
Yes, yes. You guys could minimize.
Thanks. Good morning, everyone. I hope I am audible. You have started for that online people. So if you actually can't hear me, please raise your hand in that online, okay, so that we can recognize that some disturbance is there. So let me start by thanking Professor Shumbhat, who's really great initiative to having this kind of workshops. Okay. And I'm really grateful to him to give me this opportunity to discuss some of the elementary things of quantum computing. I know that I'm not able to cover many other things, okay. But this idea is that we'll be at least introduce you that what are the things quantum computer can do, what are the things quantum computer cannot do, okay, and what are the procedure, okay. what is the advantage? Okay. So in a linear language, I'll try to explain, but there will be some mathematics little bit. Okay. And please feel free to stop me whenever you think that it's not conveyed to you. Okay. So this idea is to that at least you have to learn or you to understand at least the procedure, how it is working. And following my discussions, it was a Mishra will discuss the application part, which actually also will look at it. Okay. So this is the I would like to also thank my collaborators, Professor Sabyashachi Mishra, Hardeep Singh's, Sonjoy Chakravarti, Subham Bhargav, who are also working on quantum. We have a large group in quantum optics, and this is a small group who are working on quantum computing. And I think all of you actually are familiar with this picture. Okay, this is that skeleton of the IBM's quantum computer, which is a dilution of refrigeration. Okay, and like that, you also may know. This is not working. One bit. Forward, it's not working. Okay. Also, one minute. Sorry. So there, I think if you are keeping the eyes on the news, there are a lot of new public and private companies. Okay, they are coming up their own product. So basically, people try to make the chips, quantum chips, okay, which can actually produce like classical computation, what actually on the motherboard we use it, okay, and people are trying to make that quantum chips where actually quantum calculation can be done. And we actually there is a lot of problems as you see that there are a lot of problems when you do in quantum mechanics, okay, and we are trying to overcome this. So this is from the Google's endeavor. Okay, and I think there's a lot of hype from the Microsoft. Okay, they have talked about that million qubits quantum chips, which is known they gave the name of Majorana 1 based on the topological structure, topological systems. Okay, and there are another side. There are a lot of groups actually around the world. They are working on ion traps. Okay. So there are pros and cons in every approaches. So ion trap has the advantage that you can scale it. Okay, once you prepare it, you can mimic that an n number of times and easy to manufacture. Okay, but thing is that the total arrangement, okay, is difficult to actually put to someone else. So it's not that portable but a scalable. But there are a lot of groups actually around the world. We are working on it, and if you see that the ions, maybe you can think about this. These are the ions are actually the line, okay, in some kind of trap that is confinement, okay, which is very ultra cold. Okay, so this is kind of a chamber actually where atoms actually you can think about the atoms are confined, okay, and those actually used for your quantum computations. Similarly, that is same one which has come out from the Amazons. Okay, there is news that they also feed on the superconductor chips. Okay, that is Slater. So the Amazon's new product, okay, which we have named it Ocelot, okay, and they had actually they claimed that this will be used for quantum error corrections, okay. So this is another very hyped news from the different companies, okay. Now let's talk about that. Why you want to do quantum computation? Oh, what was wrong in the classical computation? Okay, so think about that you are solving n-body problems, okay, and your size of the system is like n particles. So you have to talk about interaction of the in particles. If you use a classical computer, what will happen as you increase the number of particles? What you see that the time it consumes to execute goes exponentially up. Whereas this claim that if you use quantum computer, it will be almost linear. So we believe that the quantum computer will come in a big relief for this kind of calculations where actually you have a multiple number of particles or many population. Okay. So with keeping it that is the goal, okay, let's see that why the lot of people, a lot of companies are investing money. Presently, if you see the market investment is around in the world, okay, around $40 billion. Okay. And big companies like IBM, Google, Microsoft, all of them, so they are jumping it, okay, like so Amazon also. And the kind of technology mostly they are using the superconducting loop technologies. Some people use mind trap, some people use topological paving technologies. And as you can see that from the news, there are a lot of work on the papers, okay, there are a lot of applications. We'll not be able to cover many of things, but even for marketing also, okay, it has been used for it. So now, where is this quantum computer in terms of the biggest scenario, which is called quantum computation? The quantum computation is one part of the quantum computations, where actually we can deal out with the different type of algorithms. Okay, we can talk about the error corrections, which we will not be able to discuss today. Okay, but there are avenues where actually you can have a lot of work. Okay, like you can work on the fundamental physics point of view. You can work on the quantum methodologies. Okay, like different kind of an experimental setup you can make it, which can be used. And there is quantum cryptography. There is a huge number of groups which are working on quantum cryptography, and certainly there are quantum computations. So today's discussion will just confine ourselves in some small region, like some few quantum computation how it works. Now, think that this idea of quantum computations, okay, came when actually that famous person, Feynman, who has actually said that we are doing all the quantum mechanics on the classical computer. Where quantum mechanics is a probabilistic things, and classical computer does deterministic calculation. So that is not that viable, though it is working. So he proposed that if you can use the quantum computer, like a computer or setup which is based on quantum mechanics, and then do the calculation, okay, I think you will be achieving much better physics, much better accuracies. Okay. So that idea was supported by the David Deutsch, and later who actually said that, okay, who developed that one prototype of this quantum computer with quantum Turing machines, okay, and that can have universal circuit quantum circuit. And that is the first demonstration that which also will be discussing how the protocol is made, that quantum computer can be achieved and that can actually beat the classical computer. So that is a big achievement. Later, it has showed, came up an idea. Okay, if you have that, like we say that monetizations, okay, we say that okay. So that is actually based on the RSA protocol. And sorry.
Introduction కదా క్యారియర్ కాన్సన్ట్రేషన్ ఉందా
Get muted. Participants.
క్యారియర్ కాన్సన్ట్రేషన్ ఉందా క్యారియర్ కాన్సన్ట్రేషన్ అంటే మళ్ళీ
Can you please mute yourself? Happens. Everything is promising. So the thing is that people should came up with idea, okay, that okay, that kind of an RSA protocol which I told, okay, which based on the factorizations. Now, if you want to do in a classical computer, it takes exponential time depending upon number of size of the factoring you are doing. Okay. But what he proposed, instead of the exponential, one can make it the polynomial time factor. So that same factorizations you can do by putting polynomial time. That is the major step, and that is the major trait also for the computation, that security purpose. Okay. So now if you can do it in polynomial time, then whatever OTP you are sending, that can be accepted. Okay. So that actually is a big challenge for the communications security problem. Okay. Further, there is a lab broker, Indian guy, who actually developed, okay, a protocol. If you have a sample of size, let's say n, okay, and you want to search your name in that, okay, what would happen that you will choose like one by one and see that whether from the sample it is matching with your name or not. That takes actually the state order of n. But what he proposed in his algorithm, it is a square root of n. So that is actually, if you think about, if you have a sample size of 100, okay, where actually your classical computer takes 100 steps and the quantum computer takes 10 steps. So that's a major achievement here. So these are they are following a lot of work on that, and they actually bring the quantum computing in limelight, and people try to realize that quantum computing will revolutionize the human future. So let's try to understand all this. Okay, little. Okay. So you may know that all of them, but let's see that what is the quantum computer does. Okay, so quantum computer, okay, if you just understand, it's like a machine which performs the calculations based on the law of quantum mechanics. And what is quantum mechanics? It actually describes the behavior of the particles at the subatomic. Think about the atoms which has electrons. Yes. And the electron, what is the structure of electron, what is the configurations, and what is the dynamics of the electron. Okay, that can be understood in the quantum mechanics. Okay, so that all the subatomic so all the subatomic physics, okay, can be understood by the quantum mechanics. Now, once you say that discussing the subatomic systems, okay, now how do we deal with those systems? How do I understand the systems, where it is, how it behaves, all those characteristics? Okay. So for that, what we actually develop a new approach based on the linear vector space, not linear algebra, linear vector space, which actually has some kind of constraint known as Riemann space. Okay. And you know that vector space, okay, has elements like you have a real vector space, okay, and 1, 2, 3 are the element of the real vector space, or half is the element of the real vector space. Similarly, you can have any element which is actually belongs to the Hilbert space can be actually assigned here at the pointer stage. Okay. Now, so let's say that we are just denoting by those states. There is a notation here by Psi in some kind of structure which is known as Dirac structure, okay, Dirac notations, okay, and this is Tate notation which we say, and that is the way we define the quantum state. But as I said, this is abstract. Is there any physical meaning of that? Okay. So the question is that how to understand physical significance of this state shift. To understand that, and it is like actually you can think about in classical mechanics is a Fourier space diagram. Okay. So if you want to have any property of the particle, you can extract from them. But only thing is that you have to make a measurement. Unless you do measurement, you will not make. So that measuring system, like if you want to find a position, you make a data like electron microscope or some things, okay, to find out the position of the particle. So what you do that, do the measurement and find that at defined places, what is the probability of the electron to be there. And that actually comes from this mathematical element where actually we are writing it in the position space, okay, in the dual space of the position, okay, and this is mathematically known as linear product, and that gives a function, okay, which can be numerically available, that's psi x, and that is popularly known as wave function. Okay, and this wave function has a physical meaning. If you do the square of it, it will tell that what is the probability to find that electron at particular position x. Similarly, what we can assign that the spin degrees of freedom of the electron, this position. So if you do that, what would happen? That we will get the spin information of the electron of the particle or psi. Okay. So let's say that you have that one electron, as we know that electron can be up or spin down. Okay. So what would happen? They are actually the degenerate or same energy state. If you apply magnetic field, they can be separated in terms of energy levels. And so once they are separated, what you can understand, they can be used as a two-level system. They can be understood two-level systems. And let's say that the two levels, one will be spin up and spin down. Depending upon the what kind of a system, what kind of state you are talking about. Okay, one of them will be energetically lower, another will be high. Let's say that up one, spin up is energetically lower and spin down is energetically up. So we can actually get from one to another also. That we can make the spin from down to up or up to down using the external light. So there is one micro, you know that their energy levels are separation is very small. You can have microwave light to transform one to another. So that means if I say that if I identify that up spin and down spins are like your in terms of bits, classical bits, the 0 state and 1 state. Okay. So in quantum mechanics, we are just writing it in the Tek notations. So which is like the 0 and 1, and which is the analogy with the classical bit 0 and 1. So that means by saying that, what you know that if we have an electron which is in 0 state, I know that if you have 100 number electrons in ensemble, all the electrons will be in the ground or up spin state. 0 state. Similarly, if it is 1, it will be all the electrons will be up. Now, the beauty of the quantum mechanics comes here. It says that having an electron in the subatomic level, okay, that quantum mechanics space holds, your state can be identified, okay.
There is an audio issue.
Just about
5 minutes. Just wait, there are some audio issues. Enable echo cancellation. So what is it taking? Microphone, right?
sir, microphone.
Not real thing.
No, microphone.
Okay. So you can ask actually.
Acha.
Hello. Am I audible? Online guys?
Yes, you are audible.
Is the sound better now?
Is the sound better now? Clear?
Yes.
Yes, sir, it is pretty clearer.
Okay, thank you. Thank you. So when we talk about in the quantum mechanics, okay, these states, okay, of the electron, it can't be identified as only 0 or only 1. It can also be identified as a a linear combination of 0 and 1. It's like a split personality. You can have both the personalities together. Okay. So what would happen? Here what you can write psi, okay, you can write is the linear combination of 0 and 1 with the proper coefficients, which I can write in terms of the spin vectors. Okay. And what would happen that only condition that a square and b square has to be 1. Okay. That means that the particle is there. Okay. That the particle is present there, that's actually determined by this constraint. Okay. And what would happen? Now this electron is available both 0 and 1 position with the probability that a square will be probability for that availability, or if you do the measurement of the state in the up spin, and b square will be probability to find in the down spin. Now thing is that here comes a big advantage that now earlier your classical bit which was defined 0 and 1, okay, now using those bases 0 and 1, but keeping the different values of a and b, you can get infinite number of states. So you have the same basis 0 and 1, same up spin and down spin, but what you are just doing, you are just manipulating that 0 and 1 in some way that you are getting the linear superposition of this. So that is actually beauty of quantum mechanics, which you don't see in the classical mechanics, in the sense that in classical mechanics, if you want to see that where is the electron, you will be either tell that it will be in the 0 state, or it will be up spin state, or it will be down spin state. But here, what happens? You have a probability to say that there is a possibility that electron can be on the way going from the up spin to down spin, or it will be down spin to up spin. So that provision also is coming out. So that's the beauty of the superposition theorems, okay, in which is available only in quantum mechanics. Okay. That in classical bit you have that 0 and 1. Now when you talk about a quantum bits, which is popularly known as qubit, okay, and that can be having an example that 50% times you will be in a 0 state, up spin state, 50% times it will be down spin state, and if you write in that way, you will have a possibility to tell that 50% times it will be going from up to down, and 50% times it will be going from down to up. Similarly, you can have that possibilities that the superposition is like a 75 to 25%. So that 75% will be available in 0 state, 25% will be available in the 1 state. So that is a defined possibilities. Since these electrons, okay, which we are talking about, they are actually obey the quantum mechanics, where actually wave particle duality is present. These are called actually matter waves. So these matter waves are denoted by the quantum bits. Okay. So now if we just go for that more number of particles, if you think about it, number of electrons are raised, let's say 2, then what would happen? You will be able to define this each electron in terms of 1 qubit, and so you have a 2 qubit systems. And now you have a possibility that both the electrons are in down spin, up spin, or one up, one down, one down, one up, or both of them are down spins. Now thing is that in experiment you prepare the system where both the electrons are down spin or up spin. Okay. Now what you can do that, you can just apply external field, like I told the microwave light, and so if you say I want to make from 0, 0 to 0, 1. I'll apply single photon, which is actually make the transition of the particle, that electron, from the up spin to down spin. And then I have a possibility to get that either 0, 1 or 1, 0. Now if I target it, I want to apply in the second qubit. So I can make the particular choice. Okay. So, or if I don't have a scope to target it, I'll have both the possibilities. Okay. So both 0 and 1 0 possible. So these are the quantities that in this that 2 qubit state. Okay. So your alpha 0 0, which is coefficient for the 0 0 possibilities, that actually the square of the quantity, the probability of finding that both the electrons are up spin. Whereas that what is the probability to find that spin orientation of those electrons. Okay. So that actually gives us information that we can prepare for many number of particles like that with a different kind of spin orientations and get that increase the number of qubits. Okay. And having that kind of a 0 and 1 combinations. Now, think about that, as I said, that you apply a single photon on the ground state 0, 0, where both the electrons are out. Now, if you have the one photon available, so what you can do that photon either can act on the first qubit or it can act in the second qubit. Since there is a possibility that it can make the conversion of the first qubit of spin to ground spin, so I have the possibility that you will get 1, 0. If it is actually act on the second qubit, it will make a 0, 1. So now we get a new state which has a possibility to have that 0 and 1. So we can define this new state as this kind of a combination that size a 0, 1 and 1, 0 combination with the probability that the alpha 0 square will be the probability to having 0, 1 and alpha 1, 0 square will be probability to having in the 1, 0. Now suppose I want to measure first qubit. So there comes the another part of the quantum computations measurement. Okay. So that if you just measure the first qubit, let's say this one, okay, what I can have? So I have a like standard kind of system setup, so which actually tell that whether the electron is up spin or down spin. Now, if I just measure those using the setup, okay, and find it in either in 0 and 1. Let's say that I observe it 1. Then what would happen? The possibility of having that electron is an up spin, that possibility has gone. Okay. So the total state what you had, that 0 with a combination of 0 and 1, 0, by observing one particle in particular state, you are actually collapsing the states. So it is as if that since you are using a single electron which can actually interact either this one or this one, you are making these two particle electrons talk with each other. Okay, they talk with each other and they have understanding. If I am in up, you should be down. Okay, and I am in down, you should be up. So that kind of talking or correlation is actually communicated prior to the of the measurement is done. So that's why that superposition will be collapsed. So it's like that. If you are your friend, actually your friend is in a hostel and you are here, okay, you have understanding that if someone was to, if your teacher was to find you where you are, you will say that my friend is there. Then that your teacher will understand you are in the class. Okay, so it's like that. But you had a possibility to be there in the hostel also. So that possibility is now closed. Okay, so that is called collapse of the function when by doing the experimental measurement. So that's what you will have now. I think there is a mistake here. The qubit 2 becomes 0 only. Okay, or if you observe that this is 1, 0, then it will be 1. So this is called entanglement. That means that what you have it now, that these two particle qubits talk with each other and had an understanding. Okay, so they have understanding that how actually they should behave. Okay, where they go. And this has a big advantage in the quantum mechanics or quantum computation. This is a real beauty. So it doesn't matter, these two particles has an understanding like this, and as I said, you are in a hostel and your friend is here, he can be in anywhere else in the world, okay, and he can be here. So as soon as he was found in a particular position, the person who was observing, he knows that his friend is another position. So that depends upon the distance. Okay, you can actually find then that confirmation, the other particle measurement, just by seeing one particle, not bothering about the other particle. Okay. So that's the entanglement, and that's a real beauty of the quantum mechanics. And that can be exploited for many purposes, like faster communication, improved sensing, secure communications, which is playing a major role as people are using cryptography. They use that Eckart kind of formalisms where actually that entanglement plays a big role. So quantum teleportations, all of them actually is a big example. Yeah.
So if I have a 0 and a 1 state, so then the psi that we can construct is an infinite number of possibilities based on A and B. So then though I already have, instead of classical I have 0 and 1, here I have infinite number of things that I can give. So then what is the advantage of the 2 qubit state?
The advantage, as you see that, let's hear. Okay. So what you had actually that you have that possibility that there is a 0, 1 and 1 0 like a classical. Then there is a possibility that some particle will go from here to here and here to there. That's called as superposition, isn't it? So there are possibilities that during the measurement that some particle will be going from 0 to 1 or 1 0.
No, like that part I understand. So my question is that why I want 2? One already.
So first of all, so are you satisfied with a single qubit or single particle? That is not actually physically viable. Viable in the sense that in the world you have many particles. Okay. In terms of the physics or in terms of any description of the natural particle, you have to have one particle along with that your friend. Okay. Your friend will be always with you. You are not be isolated in the island. Okay. So then you have to talk with a friend. Your friend will disturb you, your friend will actually make you enjoyment, all those things will happen. Okay. So that understanding is necessary. When you measure when I try to understand your character, I have to understand that your friends, how he is behaving with you. Okay. So it is like that then I have to have a multiple particle. Okay. Also you see that when I have a two particle or many particles, quantum mechanics gives us advantage. I can get this kind of a system where this is entangled. Okay. And it has a superpower, okay, in many cases, okay, which you will realize. Yeah. Sorry, can we have?
Yeah, I'm saying that can we have a particle with multiple types of entanglement? Like let's say we have three particles, two of them entangled in one way and other two, like one of the particle is shared with both of them. So A and B are entangled in one way. Let's say they are entangled in the spin physical measure, and B and C are entangled in some other way.
No, thing is that. So as I said in the beginning, okay, these states when you say that, this will be in particular domain of the characteristic. So if you are talking about spin, all of them you have to be talking in spin. But now if you talk it in the position, or let's say the angular momentum, that is a different domain. That is a spatial domain, isn't it? So the spin domain and spatial domain, they are not correlated. So if you have the two different domain, if I understand your question right, okay, that you are defining one particle with a spin, one particle in the spatial domain, okay, this kind of characteristic will not be applied because they actually mathematically commute. Means that it doesn't matter that whether he is there or not because that particle is defined on the spin, other particle. Okay, so yeah.
So I am saying that let's say B had some spin angular momentum and B had some angular orbital angular momentum, right? So the orbital angular momentum, he is entangled with the C particle C,
Right.
and for the A particle, the spin part is entangled.
So you have that A, B, C. Let's say this A, B, C. So you have that spin, both of the hat. This has an orbital L and this is orbital L.
Yeah, yeah.
Yeah.
Yes.
So now you see that you want to entangle. So when you got entangle, you can entangle with this or sorry, uh, or entangle with this. Okay. But you will not never be able to entangle with this. Because
Yes,
we are
of
actually
course.
defined in different
Yeah, yeah.
space.
Yeah.
So that's
So the uppercase can be possible.
Uppercase possible.
Yeah, that's what I'm
So
asking.
that is actually is a preparation. You are preparing that your particle in the orbital angular momentum domain. Okay. It's too loud or? So there is a recent article in Physical Regulator which is well cited, and you see that is editor sessions, and this is actually one of the paper which I would recommend all of you to go through because it is written in the layman language. And what actually it tells that using entanglement you can make that strategic games. Okay, so doesn't matter where the two people are there. Okay, so that actually what this claim that using entangled particle can outperform the best known classical strategy games. Okay, so that statistically it is very applicable, and they have demonstrated in the paper. So I wish actually you should go through. So that's actually gives you a very good understanding that what is entanglement, what is its power. Now let's come back to again that what we know that classical bit, let's say this is a single, yeah.
Go back to the paper some.
So this I think you all wish to just go. Okay. So now let's go to that, our understanding that what is classical bit and quantum bit. Okay, just refresh yourself. Think about that I have a spin chain of atom. We can have a single atom with having particular spin, okay. Then we can say that, okay, what is, I don't know, what is the other directions, okay. So it will have that either 0 and 1. Similarly, you can have the 6 number of, say, 6 number of the electrons, okay. They are either up or down. Depending upon that, we can assign the bit, classical bit 0, 1, or like. So what is the possibility? I can have a 2 to the power 6 number of possible way. I can just make them alignment in the either up and down directions, isn't it? So, but having a classical bit, I'll have only one option to us among the 2 to the power 6. Now let's say the quantum bit. You have a single bit. Mic is on. Okay, I'm audible. Okay. So then when you talk about quantum bit, okay, what comes actually, you will have a same particle can have a both the possibilities that will give you the single qubit. Apart from that, what you have that now, since each of them can have the both possibilities with some probability, what would happen that you can actually gain all this 22 to the power 6 number of possibilities at a same go or single go. Instead of having only one possibility of the 2 to the power 6 here in classical period, here what you can have at a single step, you can have all the 2 to the power 6 possibilities. Okay. That's a big advantage in the quantum computation. Okay. So all the possible states can be generated in a single step. Okay. Like that, you can think about an example. So let's say that you have a 3 qubit system, 3 particles, okay, 3 atoms are here, and you are shining that external light on this microwave light. What would happen that electron can go from the ground state to excited state like that. So these actually making you like a input register. Okay. So you are preparing your state, okay, in this register. Okay. So that preparation you have to make. Okay. Now using the external field or external light, what you are doing actually, you are putting that electron from ground state to excited state. That means what you are doing, you are actually doing some operation so that your state can change it. That means it's like that you are going from 0 to 1. So that means extra operation is done and that will give you the other possibilities. So depending upon the probabilities, you can have that different possibilities like that here. You can have that almost, not almost, 8 possible way, okay, that where all the 3 atoms are in the ground state, or one of the atoms in the ground state, 2 of the ground state, one in the excited state, or other, all 8 possibilities. That is possible, okay, from here. And here what the way we have written, if you see that from the probabilistic point of view, okay, all of them have an equal probability. That is 1 upon 8. Okay. Now, using binary kind of notation, if you say 0, 0, 0 is 0, then 0, 0, 1 will be 1. Similarly, 0, 1, 0 will be 2. Okay. So, 0, 1, 1 will be 3. Okay. Like that, you can have the different numbers you can generate. Okay. In the same setup, same state preparation in a single go. In a single kind of operation, you can make it. So that's the advantage. Whereas in classical case, you have to use one steps to make each of them. Okay. So you can make, if you can start with the n qubit system, simultaneously you can make the 2 to the power n minus 1. Okay. 0 to 2 to the power n minus 1 number. Sorry. So that is a mistake here, minus 1 should be here, not in the power. Okay. So this is the big possibility of superposition in the quantum mechanics, and here the comes are quantum parallelisms. So the quantum parallelisms, which is actually major boost in the quantum technology, okay, and this is one of the examples. Now, okay, fine, we have prepared our state. It may be all the particles in the ground state. Okay. Then we saw that we can also have the other state possible, like that having the different values of xi. Okay. We can have xi can take any combination of 0 and 1, and we can create other states. Okay. Just having the different qubits. So these, each of them are corresponding to each electron you can think about, and they are aligned in a particular spin directions. Okay. And you are making the n qubit system with the n number of electrons or n number of atoms having the different orientation of the spin. Fine, sorry. Okay. Am I audible? Yeah. So, the question is that how to create that different combinations out of the prepared atoms which are all in the ground state. As I told you, you can apply the external light and you can target to the particular atom or n number of atoms, okay, and change it. So that means you can do the operation, okay, using the external field. Or if you want to suppose add 2 numbers, okay, in the XOR, okay, and then you have to write it in terms of that binary format, and each of them corresponding to each the atoms or electrons, then you just add bitwise, okay, and you will have the addition terms, and which will have a carrying term. The point is that how do it? So you have the logical circuit, isn't it, in the your classical computer, where you have performed addition, multiplication, division, some of the logical statements, many things are done. So once you prepare your input, which you are giving in a classical computer using keyboard, where in quantum mechanics we prepare the state first, okay, and then how do you perform that logical gates? Okay. So that means we need to have the quantum gate analogous to the logical gate, and the way we, as we said, we can do it using external field, external perturbation. Okay. If you just compare your classical computer with a quantum computer, what would happen? You have the prepared state, which is like input here, then you just using external field make all the quantum logic circuit then what would happen after application of external state has understood that each of the electrons can be converted or they may prefer to be stay back in that. Depending upon that, you will get a final state output. But it is there. Unless you measure it, you will not know. So that means you do have to do the measurement. And the measurement, not only once. If you do some n number of electrons, if you do one measurement, what would happen? You will get one possibilities. You will get one possibility. Okay. But that may not be right result because you are doing it probabilistic way. So you have to do 100 number of measurement and take the statistical average, which will give the final result. So that is the basic building block of the quantum computer. So now you have to know that what are the quantum gates. So when you talk about the quantum gates, okay, there are some simple things like one thing is very important that since we are doing in a quantum mechanical way, which actually is reversible, means that if I just convert up spin to down spin, there is a possibility that down spin has to be also converted to the up spin. So that it has to be like a called unitariness. Okay. So that what would happen, all this gate has to be unitary. Okay. So as I can have that, if I just choose that I don't want to do any one. Whatever state prepared, I just keep it. So that means I will use identity gate. Which means that if you are talking about a 0-1 basis, okay, so that then you can write it, this is like a format that this is 0 will be 0, 1 will go to 1. Okay. So then what you can write it in the fashion that this is my operation I identity and which has only diagonal terms. You see that is this is term and this is term. These are two diagonal. The other two terms is 0, 1, 1, 0. Okay. Those two term coefficient will be 0. Okay. So that's why that is identity operations or unit gate. Similarly, suppose I want to make such that 0 will go to 1 or 1 will go to 0. So I should have some kind of operation. Like I said that external microwave light. Okay, if I apply it for resonance frequency, what would happen? 0 will go to the 1 or 1 will go to 0. So that is the operation which we can actually understand mathematically that it will be like NOT gate, classical NOT gate. So 0 will go to 1, 1 will go to 0. So that will be able to express in this one of the Pauli matrices format, that is X matrix, which is known as X gate, okay, and which has you see the coefficient that off diagonal terms are the coefficient, diagonal terms will be 0. So that's why this is called that X gate or NOT gate. Similarly, if you want to see that I want to make the 1 to -1. Okay. So that means that I want to just have a e by I pi phase. -1 means that e by I pi. So that extra phase pi phase I am just going to add. So then what would happen that you can think about 0 will be 0, but if it is 1, it will be -1. We can have an operator in the Pauli matrix which can actually takes care of this one, that is. So these are all operated on the single atom or single electron, or you can say a single qubit. Okay. So you can use Y gate, similarly you can ask. And what you can show that Y gate is nothing but you can combine that X and Z gate and you can get Y gate. So that's why you generally don't use it separately, but you can use it. Now, are you satisfied with a single qubit gate? Are you satisfied with that one operations per particle? Okay. So then what would happen if I ask that if I find you are the same person, then you should be there. Some kind of logical statement if I just do. Okay. So that means that I have to compare with someone, or if I want to add two terms, okay, which are not 0 and 1 beyond that, that means I need actually multiple qubit operation. So that once you talk about multiple qubit operation, that means our simple example is 2 qubit gate. Like it has 4 possibilities. It is 0, 0, 1, 0, 0, 1, or 1, 1. Okay. Now, if I say that I want a logical kind of a gate that if that A and B are two actually represent two qubits, okay, and if A is 0, B will be unaltered. If A is 1, B will be altered. That means that altered means that here A and B, as you know that it has a possibility to take the value 0 and 1. So if A is
Sir, your audio is muted.
am I audible now?
Yes, sir.
Yes, sir.
Fine. So we are having some kind of controlled gate. That means that this first qubit is controlling and changes are observed in a target qubit. Okay. So this is like that. Here you are having NOT gate, but means that B is changing its flavor, but the flavor changes depends upon the value of A. Okay. So that's called it is control NOT gate. And that is very useful because now you are able to talk this two different qubits, A with the B. Okay. So let's say that I want to add two values A plus B. Okay. How do I do it quantum mechanically? Okay. So what would happen that I know that one, if A is 1, B is 0, I can add it up and get 1. But if both are 1, then I'll have a carrying value. Okay. So that has to be actually understood early. So that carrying value I am saying the C. Okay. Then what will do that? I know that these control NOT will do that XOR. So what I do that I'll first add the carry part and then add the B, A part with the B. Okay. And that will give me that binary additions. Okay. So that actually is the application, simple application of the control gate. Now you started with that state prepared in the A, B and C, you can put in 0 if you like initially, and then you see these changes. But finally what you have to do? You have to measure this state, the third qubit, to get that summation. So that actually depends upon your measurement values. Okay. There are one more gate which is very useful. That's because that as we know that we can prepare all the states are in the ground level. That means all of them are 0. But now how do I get a one state? That means if I prepare all of them are in the up spin, okay, then how do I get in down spin in that? So that means I should have some gate which actually can convert 0 to 1, or there will be linear superposition of 0 to 1. Okay. So here is a gate which is known as Hadamard gate or Walsh Hadamard transformation. Okay. So this is also unitary operations, and that depends upon if you have initial state is 0, it will make that superposition like 0 plus 1, and this is a normalization. Okay. But if it is 1, it will make 0 minus 1. Using that, what you can show that if you have this is their total matrix format of the Hadamard gate, but what would happen if you have 2 qubit cases? What you can see that if you operate that Hadamard gate for both the qubit or both the atoms, okay, then what would happen? You are gaining actually the all possible states, okay, or that is this are the 4 bases for the 2 qubit 0 0 0 1 1 0 1 1, all possible states. So using the Hadamard gate 2 times for the 2 qubit cases, you will be able to simultaneously, okay, that simultaneously you are applying, and then you will get all possible. And what would happen? All of them have equal probability. Similarly, if you want to get suppose n number of numbers, okay, and have a linear superposition of all of them, so you will apply the n times, okay, Hadamard gate, but each Hadamard gate will just operate on particular qubit, okay, and that way you can get all summation over x. So now using that one for the 2-qubit cases, what would happen that you can gain, so since you have seen that bases are 4, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1. Okay. But there is a possibility that you can get another 4 bases for the 2-qubit cases, okay, and which will be very, very in the sense that what I have talked already in terms of entanglement. So if you have that 0, 0 plus 1, 1 by root 2, this is the entangled states. Okay. And that one you can use or you can form it using the Hadamard gate and the CNOT gate, where actually if you can just work it out. So if you think about that, I think you are able to see it, 0 state, okay, and you have a Hadamard gate, okay, and you have this controlled NOT gate, and here is your 0 state, okay. So these you are controlling it, okay. Then what would happen at this level? You are having both of them are ground state. At this level, what you are having? You are having that first qubit, which is going through the Hadamard gate. It will be 0 plus 1 by root 2, and the second qubit, okay, still it is being 0. Now what would happen? That means that you are gaining that 0, 0 plus 1, 0 by root 2, isn't it? Now if you see that, if you use CNOT gate, application of CNOT gate, depending upon the first qubit value, the second qubit actually will change. That means if first qubit is 0, second qubit unaltered. That means since the first one cases, that first one is 0, second qubit is unaltered, that is 0. Whereas in the second case, okay, second possibilities, okay, this first qubit is 1, second qubit will change 0 to 1, so that will be 1. Okay, that is XOR. Okay, and then you will get this one. So what you can get, you see that you get a state which you are wanted to have, like entangled states, okay, and this one you can achieve using the Hadamard gate and CNOT gate. So this is a simple example of how to use the simple simple one body operator or one body gate or two body gate. Okay, you can get the different entangled states. Similarly, so ultimately what you have to do, you have to measure the both qubit to find out the final state. And here what would happen? Here if you do the measurement, your first qubit will have both possibility that 0 and 1. Similarly, second qubit also having both possibilities 0 and 1. So both of them having 50-50 possibilities. Okay, so that measurement will do. Similarly, so you can use the different choice of the input state, that x, y, okay, and you will get other possible basis elements, okay, and these are all of the entangled states of 2 qubit systems, and these are known as popularly Bell states, which proposed by Bell. And these are being lot of use of this. Okay, if you are in the field, you can just get it. So what would happen that if you do the measurement, what you get that this is that different value 0 and 1, okay, and if you do that 100 number of measurement of this one, okay, 50% times you will find it the first qubit is 0, okay, 50% times the first qubit will be 1. Okay. So similarly for the second qubit you can do measurement. So that's actually gives you the understanding that how you are just getting output in this simple algebra or simple operations. So let us talk about just a few minutes, 1 minute. What is the quantum supremacy? How the quantum computer will be superior, okay, than the classical computer? As you understood that so far that if you want to have a computational capacity, just that is the measuring things. So you want to suppose double the computation capacity in the classical computer from 32 bit to 64 qubit. So that what you have to do? You have to add 32 qubit, okay, with the 32 qubit to make it a 64 qubit. So that huge number of investment you have to make. Whereas in quantum computer, suppose I want to double the capacity, okay, so since it is number of qubits, okay, is small n, and that what would happen that you will get 2 to the power n number of elements, so that if you want to just double it, you have to just increase one more qubit. Okay. Just single one qubit, if you just add it up, okay, which will make that your system capacity double. So that is a big achievement in the quantum computer. Similarly, what you see the quantum parallelisms, what I have already talked about it, and what you will see now that even using the quantum algorithm, which I proposed, okay, earlier, that Deutsch algorithms, which has shown the first demonstration that how the quantum computer can be superior than any classical computer. You can assemble all the supercomputer in the world, and that can actually cannot beat the quantum computer. So one thing is very, very particular, that quantum computer will not substitute the classical computer. There are certain things, okay, where actually classical computer
Audio is muted, sir. Audio is muted.
so there your classical computer will be very good enough. Okay. So you are not going to substitute it, but there is certain class of problems, okay, which actually if you use quantum computer, it will be very useful. Like some of the example like boson sampling, okay, which classical computer takes infinite time. Even in your universe time, it can be possible to solve. But using quantum computer, you can solve it within an hour or so. Okay. So there are certain problems which will be very useful for quantum computation. Okay. And these examples were the Deutsch algorithms for the characterization of function. I'll talk about it. The Simons and Grover search algorithms. Okay. So these are search algorithms which I talked about, which is a very powerful search engine kind of thing. Okay, and which you can beat your classical computer search algorithm in terms of the speed. And other source factorization algorithms, as I was talking about, that sending the communication using the security channel, the OTP. Okay. So that if you just use source algorithm, that will actually crack. Okay. Now, just take a, I have 10 minutes, 20 minutes. So, I'm taking your time. So, I just want to describe the power of that Deutsch algorithm. Okay, just for your, because many of you are new. Okay, so let's see. So in 1985, okay, Deutsch says that suppose I have a function which takes the value from 0, 1, okay, the inputs are 0, 1, and it can convert to any values 0 and 1. Now, so if you have that from 0 to 0, or possibly 1 to 0, or for 0 input or 1 input doesn't matter, that output will be always 0. Or here if for any input 0 and 1, output is always 1. So that determines that characteristic of the function is constant function, isn't it? That whatever the input, output will be same. But you can have another option that if it is 0, then 0 and 1 will be 1. So that means you have the possibility the output can be either 0 and 1. Or you can have for 0 it will be 1, 1 it will be 0. So both the possibilities are there. That means it is balanced. Both of them having equal weightage and is balanced. So that actually gives the characteristic that the function a, whether it is a balanced or it is a constant. Now if I want to find it in classical way, how many steps do I require? Not to you. You see that if I just choose one of the options, okay, and find out putting the initial x value, that 0 and put in 1, and if I get output, then I can confirm that whether it's constant or not. Any of the options will be fine for us among the 4. So it is 2 steps, isn't it? So just I have to check that, put both the input 0 and 1, and see what is the output. Okay. So if you get both times 0, then it's constant. Both times 1, then also is constant. Or 1, 0, 1, 1. Okay. Then at least minimum 2 steps. You can use the 8 step. That is, if you have a time, you can do it. But use that minimum at least 2 steps. What that means that it doesn't matter what computer you use. You can have world-based computer. You assemble all the computers, but minimum you require 2 steps. Okay. But what Deutscher showed, using quantum algorithm, you can just find the functions characteristic in 1 step. So that's the power of this algorithm. So just let me briefly talk about it. So suppose, let's say that I have prepared my state, blue one. Oh, thank you. So let's say that I have prepared my state in the 0 and 1. So that's first things actually we have to do. You have to prepare your state. In quantum computation, you have to prepare your state. So you just say that I prepared, okay. So you can start with the both 0, okay. Now you can make that some conversion that, let's say that I am putting it is, this is 0, okay, and this is 1. So that means I am putting X gate here and a gate here, single qubit gate. Now this is my state preparation, okay. This is a state preparation. Now what do I have to do? I have to find that these are the 2 inputs, 0 and 1, okay, and I have to operate them the function f, so that I can get output, so that I will have applied some external field which is mimicking the function f, which has to actually represent the function f, and such that from the output I will get the expected result. So the thing is which is done here, so you started with the psi naught, the initial state is 0 and 1. Okay, that is. Now, what you do, you started with that, so I'm just taking one step below, 0 and 1, and then you operate, what gate you operate and get this one? Can you just tell me? What gate I should operate here and get the expected state here? 2 Hadamard gates. If I operate Hadamard here, you see that I will get for 0, it will be 0 plus 1 by root 2. For 1, it will be 0 minus 1 by root 2, which will give me that half factor outside, and you will have first qubit is 0, second qubit is 0, that option. Then first qubit is 0, second qubit 1, that is 0, 1. You have first qubit 1, second qubit 0, plus 1, 0, and first qubit 1, second qubit 1, 1. So that is the 2 Hadamard gate. If I apply, I will get the expected state here. Now, if I get expected state, what I have to do? I have to use some, okay, some operation. Now, this operation, you see that this operation is depending upon the, and what I have done here, so using that one, if you just look at carefully, I have made both the possible of the first qubit. Both 0 is possible and 1 is possible. Okay. Now, if I just make the function available to the system, that means I will apply some field, okay, so that this which will mimic the function, then this will take the first qubit as the input, or it is controlled, control state, okay, or control bit, and will use the second qubit is the target qubit. So that means that depending upon the value of this one, okay, what I'll have any value, because I can have both 0 and 1 here, and here, suppose I was having here y, then after operating UF, what I get? I'll get X back,
and here it will be y XOR fx, or you can say that y fx. Is it clear? So that I am operating some field here, okay, and which makes that takes this is a controlled one. Depending upon the value of x, it will add in the second qubit the, it's like a controlled one, okay, control gates, okay. So that it will just add XOR with the whatever second qubit is there, that will. So if I do it like that, what you see that from xy I get xy plus fx. So now if I apply this UF on this state, UF, what I'll get? I'll get 0, f of 0, because it is 0 plus f0. So I can write it 0 plus f0. Similarly, I'll have a 0, 1 plus f0, because it gives out x is 0. Then I'll get 1, 0 plus f of 1. Then I'll get minus of 1, I'll get 1 plus f of 1. So that is the things which I wrote it here. Okay. Now if you see that, if I use this understanding that this f of 0, as we see that it takes the input value and give you the output, which is also in 0 and 1, isn't it? So that it depends upon, so if since this is 0, so this total value will be f of 0, because because if you add it with the 0 values, it will not change. Similarly, if we add it here, what would happen? Depending upon the f0 value is 0 and 1, 1 will be added with that. If f0 is 0, then this will be 1. If f0 is 1, this will be 1 plus 1. That will be 0. So that means that whatever the value of f0, it actually gives opposite to that. So I can write it that f bar 0. It will give f bar 0. Or negation sign, you can use it. Okay, that is the negation sign. Similarly, this will give me f of 0, sorry, f of 1, and this will give me f bar 1. Okay. So that means that what I got it, okay, after operating this one, okay, here in this state, let me talk about this is my, if it is psi 0 at this stage, okay, we tell this is psi 0 according to my slides. So this will be my psi 1 is equal to this one. Now you see that if I just if I use, okay, on psi 1 is this one. Now if I use psi 2, which actually we obtained by operating the Hadamard gate on first qubit. So that I just take it little here, so that I am operating that Hadamard gate on first qubit, keeping the second qubit unaltered. Okay, that is from the psi 2, psi 1, we get psi 2. So then the psi 2 will be, so again I'll have like 0 will be 0 plus 1 by root 2, or both of them, 1 will be 0 minus 1 by root 2. So I get that first qubit actually is a combination of 0 plus 1 and 0 minus 1. So what we'll have, just let me complete it, is 0 plus 1. So 1 root 2 will come here, okay. This is, and with the f0. Then we'll have minus sign, okay. We'll have 0 plus 1 by root root 2 is taken care of outside. Okay, so let me put it 0. And this will be f of 0, no, bar, f of 0 bar. So plus you will have, just can you help me, that this will be 0 minus 1. Okay, then this will be f of 1. F of 1. Then I will have minus sign, we will have a 0 minus 1, and this will be f bar 1. Isn't it? F bar 1. If you just see carefully, that you will get this. Now what I'll do, I'll take the terms which is having the first qubit is with a 0. And say that my function, let's say function is constant. Constant. Function is constant. That means that doesn't matter whether it's f0 or f1, the final output is same. Okay. So I can say that this is 0 and this will be, with a 0 it will be f bar. So that is f, this is f of 0 minus f0 bar, and with a 0, f1 is f0. So that is one term has come. Okay, then this f bar, this is the f0 bar with a negative sign. So both the terms will be same, and the 2 times of this quantity is coming. Just check it for 0. So f0 bar is, I am keeping it minus sign for 0. Okay. F0, f1 bar actually f0 bar. For 0 actually I am getting this one, but for 1, what you can see that 1 f0 and f0 bar, then this one, for since there is a minus sign here, f0 and f1 will cancel because f is constant. Similarly, f0 bar and f1 bar will be cancelled because f is constant. So ultimately, this will be 0. You will not get anything for the second. If it is 1, first qubit is 1, then you will not get anything in the second qubit. What means that? That means you will get 1 upon root 2, and we will have a 0 and f0 minus f0 bar. Similarly, if function is balanced, what you will get? You will get 1 upon that psi 2 will be 1 upon root 2. You will have that 1 with f0. You can check, it will be minus f0 bar. Now the beauty is that, so I get here, after doing this Hadamard gate, okay, in the first one, so this is my quantum circuit, and I do the measurement, okay. So I do the measurement of the first one itself. I don't bother about what is the second qubit. I do the measurement first one and see that if I get 0, I will tell that the function is constant. If I get 1, function is balanced. So using a single step of measurement, I will be able to tell the function is constant or balanced. Unlike classical case, I have to use 2. So that's all because I am actually able to create this state. Since I am able to create this state, which is a superposed state, purely coming from quantum mechanics, I got this advantage. So this is one of the power, okay, which David Deutsch actually showed, that doesn't matter what classical computer you use, okay, you will get, okay, you will gain the supremacy in the quantum computation. You can apply that different algorithms, which is known as Gromov algorithms or Fruit's algorithms. There are a lot of algorithms out there. Okay. Actually, everything is actually, also you can use it, Fourier transformations, okay, all those things you can apply. Okay. Just to have a continuation for the second presentation, like that what we have talked about, okay, that we can have a different algorithm for kind of an algebra, linear and nonlinear algebras, okay. We can also able to solve dynamical systems. So that if you want to have that quantum system, certainly we are talking about quantum. So if you have a quantum system, it will have that the minimum energy possible states, because this is a quantum system. Okay. Energies will be quantized. There will be first state of state, second state of state. There are a lot of possibilities. Like think of that you can think about that you have that n number of electrons. Let's say here 5. Okay. And they have only freedom that they can have a spin jet plus or up, plus or minus, up or down. Then what would happen? You can have a configuration that all the spins are up, all the spin down, or arbitrarily changed. So these are giving you, if you have a magnetic field present there, what would happen? These will give you different energy levels. If all of them are, so if you consider that no interaction is there among them, okay, then what would happen? All of them are up, that will be your down state. If you have the one of them up and if you have the one of them are down and all of them up, okay, there are how many possibilities? 5 possibilities. Those 5 will be first state. They are decayed state. Okay. Similarly, you can get that different energy levels, okay, of the system, quantum systems. And that means that since you are talking about energies, and that means that these energies you obtain from the some operators which you do measurement. And the operators, okay, is from the classical mechanics. Okay, you know that the people have used Hamiltonian approach. Okay, so they have already idea that a Hamiltonian can describe the systems. We also can describe the system quantum mechanically using Hamiltonian. And that is nothing but we already know from classical mechanics is kinetic energy plus potential energy. Okay. So the Hamiltonian has to be written down for any quantum system. To know that it's exactly what is the structure, okay, where the state is, whether in ground state or accelerated state, or if you apply some external field, perturbations, where it can go. So if you want to know the dynamics also, okay, that also has to be put in the Hamiltonian and then describe it. So Hamiltonian is one of the things in quantum mechanics which is the first thing you have to write it down to describe the systems. Like I am giving an example that same spin systems, if you think that all the spins are in actually along the z directions, and they can have that possibility to talk to each other, okay, so that electron can hop or go from one to another or interact. And if I just say that it can only interact to the nearest neighbor, then I can have that SM, the spin operator of one particle with interact with the spin operator of the next or neighbor atoms. Okay. So that will be describing that kinetic part of the Hamiltonian. So this is a simple example, okay, which actually you understand that describe the several systems. And by knowing that, what actually we want to know that what will be the energy of state. Fortunately, Schrodinger has given us the prescription. So which is that Schrodinger equations, okay, and these equation in time can't see this down. No? How to minimize this? Okay. Yeah. So the thing is that now, what is the equation if I just make it so in a time independent way, then we can write it simple form like that Hamiltonian operating on any states described by the system will give you the energy of the systems, which is the eigenvalue of the equations, okay, and your state will be unchanged. That means that Hamiltonian is a operator, okay, which give you the eigenstate. That means state whatever you actually operating on, that state is unchanged, but you will get that the eigenvalue, which is nothing but the energies. And that energy you can calculate in mathematical way. Just if you multiply the psi in a dual space like inner product, okay, and take this as a kind of expectation value, which you can write in the integration format if you like, okay. And then what is objective is that we have to minimize this energy, okay, to get the ground state. As we know that the energy of the ground state configurations, okay, will be minimum. So that actually tell me the thing that your Hamiltonian, okay, which is describe the systems, okay, if you can have the eigenvalue solution kind of things, then you will get energies which you have to minimum. Now, since the psi is described in that Hilbert space, where actually, as I said, that you can have a different kind of a configuration of the spin, okay. So all these are actually distinct possibilities. So what we can write that your any arbitrary state psi is a linear superposition of all the possibilities. So that means what I can write that this is from its basis set, and that all this possible configuration I am writing chi. So psi is written as summation of Ci chi. So what is this? So you will get that chi is like that, different kind of possibilities. Okay. So you have 4 qubit systems. Okay. Now objective will be that for given a psi which I have written in this format, that which actually give me the energies. Now I want to find the possible value of C such that, okay, that E is minimum. And if you think that they don't talk each other, okay, and that I know, for example, that C of 1, that first configuration, or C0, whatever, this will be your minimum energy state. Okay, so that means this will be coefficient of this will be 1, rest of them will be 0. So that is the example of the coefficient C. So that means that for a state, minimum energy state, I have to optimize such that Ci has to be, okay, the fitting for the minimum energy values. And here, when I do it, what would happen that I have an advantage here that I prepared my states in a spin state. And my Hamiltonian are described by the spin operators. So I have advantage to operations, okay, that I can operate these spin operators on this spin state and get different possibilities. So I can use the spin degrees of freedom advantage. And that I will try to get that energy from this by optimizing this coefficient. Okay. So that what actually this does, what is the objective here, if you prepare your state in a spin state, you have to somehow make that Hamiltonian in the spin format. That means that you use the operator in the Pauli matrices. So somehow you have to make that your whatever Hamiltonian is there in terms of Pauli matrices. Okay. 1 minute. So what would happen that I have to minimize this energy, okay, and to get this coefficients, which will give me that ultimately that what is the psi. Okay. So that this gives me the cost function. So I have to minimize the energy. And so what I have to do that as I said that I wrote psi is in terms of that basis, okay, and these parameters in quantum mechanics, what I can do that, Ci's, okay, I is reflected in the some kind of a phi or parameter theta. Theta can be theta 1, theta 2, theta 3, like that. So what I have, I can have started with that all ground state, all of them aligned, and put some that rotation gate, okay, along rotation gates, okay, of each qubit, and then what would happen, each qubit will be actually dependent on parameter theta naught, and I can make the phi state out of this, and that I can assume as the initial guess for the phi. So I need to, doing that I have to get initial guess. That is a trial function, and that's actually answers. So that you can use a different answers, okay, depending upon answers you are getting. So your answers is very away from the original things, you will never get the convergence result. So you have to have a good answer. And finally, what we have to do? We have to measure the energy. The expectation value, you have to do it quantum mechanically. Now, once you do that energy, then that energy we have to feed it, okay, measure it, feed it, okay, in the optimizers, okay, to run in the classical computer. So here is the hybrid approach. These matrix element, okay, we are using the quantum computer calculating, okay, which is actually difficult part because that gives you numerical value, but that actually is a system dependent, which is quantum mechanical system. Okay. So these we actually exploiting quantum computer for that. But rest optimizer I can use it, the classical computer and feed it. And optimizer will generate the new set of thetas for each time to get the lower energy compared to started with. Okay. So that is the way we can actually optimize the thetas, okay, and get the psi. But the first target is that we have to just get the energy. So in this paper, Harsip has, Sabyashachi, they have shown that the architecture, okay, that if you started with that initial prepared state, then you just choose your answer, okay, as I said, and that answer you will give that parameterized dependent circuit, okay, that these all the qubits will be parameter dependent, and that actually you use to exploit that operator on that whatever the operator here is, this is a Hamiltonian operator you use, and output whatever you get, after getting the output, you measure individual qubit, okay, and get that energy values. Okay. That energy values, okay, what will happen that that you will put in the classical computer, okay, and then find out what will be the best possible theta. Feed it back here, okay, and try to get convergence in this process, which is actually giving you ultimate ground state. So that is a technique which has been used. And so far, in the world, actually, you see that this is up to 2020. That number of qubits is not changed much, but there are some people have gone larger number of qubits. Okay, that is a structure. Actually, number of qubits people have used over the years. Okay, they have put many manufacturers. There are different languages has been used. Okay, so this is an old one, picture 2018. Okay, the Qiskit one is one of the very popular, which actually we also uses. There are different other languages also. You can just look at it. Listen to what that this is the quantum computation with the artificial intelligence that will actually superpower human being. So that is the target people are looking at, like Google and other things are working on it. Okay. So these are the few books. If you just like, you can just take a reference. Okay, for your starting point. Okay, I think I'd like to give you all your kind attentions. Okay, and would like to take one or two. Or maybe I think I am overshooting time. At the end, I think we'll have it. Already 11:30. Online people also can ask.
Yeah. Uh,
Yeah, I can hear you.
no, online people can raise hand and ask questions or unmute themselves one by one. So there is one question. Can you show the slide of books once again? Microphone closer, please.
That I would like to recommend this book, Nakahara and Ohomi's books, to go through because this is very elementary way written. All the steps are given, and then you can just follow the other book. And Nelson and Chuang was the first book written on quantum computation, quantum information, and I also didn't believe that at the earlier stage of 1990, okay, how they could think most of the modern technologies or modern algorithm which you are doing, they could think about that. So that is a very Bible kind of book, okay. So that you can go through at the end maybe.
Yeah, the other question is, sir, how quantum computing is different from genetic programming?
Yeah.
Okay.
So I think that the terminology is a little confusing. Genetic programming means the what?
No, genetic programming means is a meaning about soft computing. Sudhakar, you can write by genetic programming. What do you mean? Soft computing. So I think soft computing is Professor Majumdar, if you want to answer.
Yeah.
Soft computing and
It's
quantum computing.
subcomputing, as you know that
Yeah,
you can
yeah.
have your systems, okay, where actually you can build up like I'm saying DNA computing, okay, as an example, which is one of the hype in present day, okay, and it will be actually like quantum computing, it will be a future of the computation technology, okay. So you can have that is a different, so that architectures is different, okay. So like you can take the different structure of the DNA as a basis, okay, and do the computations. So that is the way actually it is different from the subcomputing. But where actually classical picture is taken, not quantum picture.
Okay, which book should we start with?
Oh, that I already said that Nakahara and Omi's books, the first one in this leftmost one will be useful.
What are
Which
the
I,
problem? Okay.
sorry.
Yeah. What are the problems that cannot be solved with quantum computing, or where classical computing will work better?
Definitely. So that's a very good question. I also told like some of the same problems. Okay, like if you want to solve set of linear equations, as an example, okay, you can use that quantum computer like quantum Fourier transformation, okay, to solve it. But it will be more expensive compared to the classical computer, which you can solve it in a step. Okay. So in that sense that there are certain things actually where you do not require quantum computer. Okay. Your classical computer is sufficient. I don't think we want to invest money and time for the quantum computer for that. Is my answer is conveyable? Understood?
Yeah. Yeah. Is there anybody? I think, yeah. I have, there is some question. Just 1 minute.
One time, physical audience.
Yeah. Yeah. No, there is one question. I have questions recently. MS have come with Majorana one quantum computer processor. What
Majorana 1.
algorithm?
Yeah.
Majorana one. Yes.
Majorana
So
1
what is
actually,
this?
Majorana 1 is developed by the Microsoft. That's chip, okay, based on that topological circuit, okay. So if you have a topological material, okay, you can use the topological material to be making qubit, okay, and so that you can have a base. On top of that, you have a topological kind of a lattice kind of things, okay, which you can just embed on that base, okay, and then you can like electron hopping, okay, as I was talking about an example, you can have the topological system generated using this hopping or some kind of a operations, okay, and that makes your topological, this is like a topological system is that, as you know that topology has an advantage, that this is an invariant, okay, for kind of transformation. Like if you have a winding numbers, okay, if you have some parameters, which you can think of that is invariant with respect to transformation. So those are like a stable systems. Like you can have a vortex. you can have a water, okay? Water, and you can make a cloth and make the water to rotate, which is looks like a vortex, okay? And you can create this kind of a vortex in the light, okay? Or you can create vortex in the fluid, it can be quantum fluid also. Then these will be topological systems. And this has the advantage that the property of it can be coherent for a long time. And that is the building block, or that is the first criteria, that you have to have a coherent state. Because during the computation, if something value changes, then you don't know whether your calculation is right or not. So the value should not change. And it should be that means that you have a long coherence time, okay, for this one. And that is one of the problem in quantum computer. Keeping a system coherent for a long time is a very challenging thing, okay. And also that you know that there is an ambience which makes the system decoherent, okay, so which you have to be taken care of, and that makes that error corrections. So there you can have a fault tolerant quantum computer, okay. Fault tolerant means that you have a long coherence times if you can make, so that during this time you can't have the, let's say, bit flip. 0 will not be converted to 1, 1 will not be converted to 0. Okay, this kind of system will be fault tolerant. Okay, so if you can make your system coherent for a long time, or whatever that operation you do, it is exact. Okay, then you can get rid of many of the noise or error corrections. So people are trying to build a fault tolerant circuit or kind of devices, okay, which will be useful for quantum computing.
Okay, so the other questions are, one student asked that whether presentation and the learning materials can be uploaded.
It's there.
Okay,
It will be
yeah,
available.
okay. Yeah, recently, no, so wait a minute. What happens if we apply Grover's algorithm recursively? Would it further speed up search problems or break quantum mechanics?
There is a lot of work going on. Okay, that you can actually embed the Grover algorithm in the source algorithm. Okay, the source, the factorizations. Okay, whatever that algorithm is there. Okay, I don't want to get in that, but you can add up the search engine algorithm in that source algorithm and make things faster. So there are a lot of papers out there. You can just look at it, if you like.
Why classical computation takes less computation for small system size than quantum computation? Why we get advantage of quantum computation after certain system size?
Yes. So thing is that if you see that plot in the initial I showed, okay, that you require that the time is that you have to prepare the state. Okay. So here, not like that. Not like the classical computer from the keyboard. You get the input, and that you have a circuit. The classical circuit, the logic gates are there, and which will the ICs are there, which will make the executions. Here you have to have the prepare the state, and then once the state is prepared, then you apply external field, okay, and then you have to measure, and the measurement is not one. If you increase the number of measurement, okay, what would happen? Your result accuracy will be improved. So that means that unlike the classical computer where in a one measurement or one calculation you can get result, okay, here you have to do that several thousand times you have to do measurement. Okay, then you will get a result. So that you have to actually taken care of. Okay, so there some of the cases where actually like if you have a really complicated systems, then like number of bodies are large, then your classical computer will take time. In that cases, once you prepare the state, okay, then you execute in the quantum computer, it will be much faster. Okay, and for the other cases, it's not that true.
Okay. Then I'll take one question, and then there is one candidate who wants to ask, one participant who wants to ask it over mic. But before that, and the other questions, I think Professor Majumdar will share it with him. He can answer it, and then we'll post it in the chat box in the later half.
That's better.
Yeah. Explain no cloning theorem. One question is that explain no cloning theorem.
Okay, in the one sentence I say, Suppose you prepare an atom in the ground state. Okay. Now you have two particle. Okay. So can you prepare that same state in the second particle? Definitely you can prepare the second particle also in the ground state. Okay. So that is means that it is you are xeroxing the particle, first particle in the second particle state. But think about that, this first particle has a combination of the 0 and 1, the A0 plus B1. Now, if you have A0 plus B1, and if you want to copy the same thing in the second particle, okay, so that what you can show that you will not get the same A and B value. You get a combination of the 0 and 1, but you will get different values. Never possible to get this. Once you know that what is the value of A and B, that means that the first particle, that superposed state, is collapsed. Okay. So once you collapsed it, then you don't know that what will be second particle. Okay. So that's the beauty of this. So, and that's actually very important point for the quantum security. Okay. You can't copy the state. You have to destroy the state and then you have to copy it.
Yeah, so I think that participant has written the question. We say that this is from Anirban Mandal. We say that quantum computers will be better at simulating the nature-like quantum systems, but in most of the quantum programming language like Qiskit, all the operations we do are by basic elementary qubit operations by quantum gates. So would it be done?
So if I understand the question correctly, so he is asking that, can you repeat it once again?
Anirban, do you want to unmute yourself?
Am I audible, sir?
Yes, please.
Okay, so I was asking that like what we say the quantum computers will be better at simulating the like natural things like suppose molecular simulation and something like that. But like whatever we do in quantum programming languages like Qiskit or Circ, are most of the things are done by like elementary quantum operations like using quantum gates, like sir as you said earlier. But then how we are going to actually simulate the things by that basic operations? I wanted to ask.
Very good questions. You have to wait for the second presentations. Okay.
Okay, sir.
Thing is that because in the common audience, I have given simplest examples. Okay, here. Okay, and if you just wait few minutes, you'll get your answer.
Okay. Okay, so I think if there are few other questions, then probably you can write it. But maybe this is a valid, important question: how to map physical problem to quantum circuit. But let us see your views.
Yes. So the thing is that, like I said, that you just first of all sketch out what are the operation you want to make, like addition, multiplication, or you want to just do the kind of logical operations. Okay. So that you have to sketch it out first, and you have available that circuits. Okay, a rotation gate, or you have Hadamard gate, control gate. I didn't talk about that much complicated gate, which actually can be boiled down to the simple gates like 1 qubit gate or CNOT gate. Okay. So once you know that what are the operation you want to do, you can sketch out and find out what are the suitable quantum gates used for them. Okay. And then you can just make the structure that draw the quantum circuit.
Two students asked that fuzzy and quantum, do they have any link? Because both of them use probability.
Sorry. What is the other
Is
one?
there any link between fuzzy logic and quantum computation?
No, there's no link. Both actually probabilistic. Okay, fuzzy logic is also the probabilistic, but that architecture is not quantum. It is classical. Okay, so if you have that, okay, state, okay, so you can use the fuzzy logic idea to calculate, theoretically calculate the quantum system, but architecture wise, okay, that you have to build up the quantum computer, which is actually probabilistic. But fuzzy logic, actually, what would happen that your structure wise is classical. Okay, you can actually inbuild, try to understand the fuzzy logic in the same probabilistic way.
Okay, I think if there are any other questions, you write in the chat box and Professor Majumdar will share the replies soon. But over to the room, if any of the students, physical participating students have questions.
Yes, sir. Sir, actually, I want to ask in the classical computer, we have memory, right? So here the bits are 0 and 1. But in the case of quantum computing, there are qubits. So which can be either 0 or 1 at the same time. So I have one question. Can there be some malwares or other thing that can impact the state of a qubit?
So your question is that how the quantum computer can be used to store the memories. And that means most important pointer, if you just make the state, okay, can you retrieve the state? Memory means what? You just write it in the your hard disk, okay, and whenever you require, you can just find it what you have written, okay. So in quantum computer also, okay, you have a procedure like the same way you would develop that imprinting that data in the quantum system, like from the state preparation, you put the field and then make the state, okay, where that your information. Suppose I will just give me an example. Suppose you have a, you are having a beam of photons, okay. Now you want to have the information inbuilt in it. So what I generally people do that they use a chopper, okay. So suppose I say that I want to put 0, 1, 2, 3, 4, 5 like that. So the depending upon frequency, okay, over time, what would happen? 0, 1, 2 will be done. And so what would happen in output state, if you see over time domain, okay, what would happen? There is some kind of signals are coming up and down. And these signals actually frequencies are changing. Okay. So that actually give you that information of the whatever input you have actually, whatever information you have embedded. Now you do that Fourier transformation of this. Okay. So you will get in the frequency domain what are the different frequency you have used. So you get back. So similar things can be done in the quantum system. Okay. You can just as I showed that you can imprint that information or using quantum gate. Same kind of quantum gate, since reversible process. Okay. You can use it again to get it back. So ultimately it is a unitary operator, isn't it? So if you operate it again, you will get back. Like if you operate Hadamard gate, okay, Hadamard gate on the 0 state, what you will get? 0 plus 1 by root 2. You operate it once again, what you will get? You will get 0. Okay. So that you can get it back. So but you have to make sure whatever operation that is unitary. Last question.
So like I want to ask, can you repeat that for a 2 qubit system, the application of the Hadamard gate?
So you can just see it easily that if you operate 2 qubit systems, so if you have a 2 qubit system, let's say x, y. In x and y can take 0 and 1 values. If you operate Hadamard gate for both of them, what you will get here? This will be output, if you just see, this will be 0 plus minus 1 to the power x 1 by root 2, isn't it? And this will be 0 plus minus 1 to the power y 1 by root 2. So what is the final state? Final state will be, it will be half 0, 0 plus minus 1 to the power x 1, 0 plus minus 1 to the power y 0, 1 plus minus 1 to the power x dot y. Okay, so x dot y actually bitwise multiplication, isn't it? That will be 1, 1. So that is the 2 Hadamard gate if you apply. Okay. Now depending on the value of x, you can get the different thing. I think, Professor Rai, I think all the questions are done. I am taking too long time, so I think Sabyashachi will start. Professor Rai?
Sorry. Thank you, Professor Majumdar, for this talk. And we can see that the enthusiasm among the participants, large number of participants kept on asking questions. So I have shared some of the questions we could not take at this time with you. And once you write the answers, I'll put it there later. Now we can take maybe a 10 minutes break and then we can come to the next topic where there will be more discussion.
chai, everything is there. So maybe 10 minutes break, and participants, online participants, please wait, and after 10 minutes we'll start the next talk. Thank you.
Participants, welcome back to the workshop. So the second The second instructor for this workshop is Professor Sabyashachi Mishra from Department of Chemistry, IIT Kharagpur. He obtained his PhD from the Technical University of Munich, Germany in 2006. Then he did a couple of postdocs. First one is at the University of Basel, and the second one is at Zurich, Switzerland, before joining as a faculty at Department of Chemistry in 2012, where currently he is an associate professor. His research interests include the applications of quantum chemistry and molecular dynamic simulations to molecules and biomolecules. Recently, he has been actively pursuing research on the quantum computation of molecular materials. So, Professor Sabyashachi, so stage is yours.
Thank you, Sandeep. I hope I am audible. Now, so let's begin. So, in this part of the workshop, we would actually, there were some questions. One student, I think Arindam, he asked that we are trying to say that quantum computer is for simulating the natural system, but where are they? So that would come. So the idea is actually what Professor Majumdar showed you on the board, I would make you do it on a computer. So there are a few caveats. We would be using the language of a quantum computer, but we will not run them on a quantum computer. Instead, what we will do is that we will run our program, which is written in the language that a quantum computer will understand. We will run this program on what is called a simulator. The simulator that we are going to use is from IBM. The language that we are, or the module that we are going to use is called Qiskit. It's a kit to do this quantum computing type of work. That's what we do. I am a chemist. I deal with molecules, biomolecules. So all my discussion, I would actually try to bring you to the realm of molecular world. So I hope you, some of, if you remember your chemistry, that's well, but at least I need atom, structure, electrons, this much background for my presentation. Okay, so before I jump the gun, so we have, as Professor Majumdar said, both he and myself, we have separate groups working on different problems, but we collaborate on this type of problems because I don't know much on quantum computing. I know a bit on chemistry and quantum chemistry, and I want to do quantum chemistry on a quantum computer, right? So we are trying to build a joint group around this theme, and this is where the people, so Harshdeep and Shubham, are jointly working with us on this type of problems, and from them we have understood a lot of things, and that's some of which I am going to present. Now, a statement that is extremely helpful in picturizing this quantum advantage is given by Feynman in 1982. He says that nature is not classical. So if you want to simulate nature through a machine that is running on classical principle, there is going to be an upper limit or a glass ceiling that will hit. How? Let's see. Suppose I have one electron. A system that has one electron is hydrogen atom. That electron can be either upspin or downspin, right? So two states. Now introduce a second electron, helium atom. Now when the first electron is upspin, the second can be up or down. When the first electron is down, the second can be up and down. So immediately I got 2 into 2, 4 number of states. Now bring 3. 2 to the power 3, 8 number of states. Now let's talk about a realistic molecule, water. One water has 10 electrons. How many pieces of information you need? 10 electrons. So I need 2 to the power 10. Do you know what is the value of 2 to the power 10? 1024, 1000 bits, not much, manageable. Now, what's the size of, what's the memory of your mobile phone? 128 GB. So a GB has how many bits? Gigabit is 10 to the power 9, right? Mega giga, 10 to the power 9. So 10 to the power 9 is equivalent to 2 to the power what? How many electrons can I have which will account for 10 to the power 9 gigabit, 10 to the power 9 bit? So if I do 2 to the power 40, that comes about 10 to the power 12. 40 electrons, which system? Benzene, C6H6, 36 plus 6, 42 electrons. So with 42 electrons, a benzene molecule enough to destroy my capacity of my phone, 128 GB. Now come to a supercomputer that we have the downstairs. How many what is the disk space? So Sandeep will tell me.
Disk space 2 petabyte.
2 petabyte. Peta is 10 to the power 10 to the power 15. So I just before that I calculated, if I take 2 to the power 60, that becomes 10 to the power 20. 2 to the power 60 is 10 to the power 20. So if 60 electron means what? Even 2 chlorine atom, chlorine molecule Cl2 has 35 plus 30, chlorine is 17, right? 7, okay. So that is 35. If you take 2 bromine Br2, that's already, that can have more number of states that our supercomputer can store. Now I am talking about nature, protein, thousands of electrons. But if I have to store the information of thousands of electrons, I need 2 to the power 1000 because they exist in those many states. They are quantum mechanical in nature. Nature is quantum mechanical. The particles that we are dealing with are quantum mechanical. So already I am hitting the glass ceiling when I am talking about benzene, bromine and small stuffs. So when I go for proteins, when I go for materials, the number of possibilities are endless. So this is what the exponential growth is. 2 to the power n. Now what quantum computer can do, what Professor Majumdar said, if I go from 2 qubit to 3 qubit, I already have a jump from 4 to 8. From 3 qubit to 10 qubit, 3 qubit has 8 states, 10 qubit has 1000 states. So 7 qubit difference, 3 orders of magnitude in number of bits. So that is the power of scaling. So you can simultaneously access a large number of states with fewer number of qubits, right? But the trouble is that these qubits are very hard to control. They change their state, they change their mind. So the best example, I come from a background which had nothing to do with quantum computing, so I found it very hard. So some examples that help me keep my head wrapped around things are the following. A classical bit is like a switch. Switch is on or off. You switch on, camera is on, switch it off, camera is off. A quantum can stay both at on and off and many states in between. Right? You don't know whether your camera is on or off. That's a tricky thing. It can give you many states, but when you measure whether then it collapses either to the on state or to the off state. That's the realm where we are talking. Okay. Now, there are 2 central equations in quantum mechanics that bothers me. When I started doing this, I wanted my computer to solve these 2 equations. The first equation is called expectation value. Why do I study natural system, molecular system? I want to extract some information from the molecule. A molecule, what is your energy? Molecule, what's your dipole moment? Molecule, what's your electron, what is your kinetic energy? This kind of information. The question that I am asking is given by this operator A. In the first equation, it's in the middle. The state of my molecule is what is called psi, the wave function. That's in quantum mechanics. So if you prepare a system, make a measurement corresponding to its energy, that's the Hamiltonian operator, what comes out is your energy. That's quantum mechanics first lesson, right? That's my first equation. The second that I want to do is that if I know the wave function now, at a later time, how would the wave function change? So evolution of the wave function or evolution of the state with time, that I can get using Schrodinger's time dependent equation, which simply tells that if I have the initial state psi 0 and I apply this time evolution operator, which is e to the power minus iht, h is again the Hamiltonian operator. So I need to know these 2 things, and practically more or less most of my requirements are done from coming from chemistry background. Yeah. These two equations we will try to solve. So always you remember that I have this wave function that I will create. I will have an operator. Operator asks the question, what do you want to know about the system? Wave function prepares the system. On which system you want to know? Hydrogen molecule, lithium atom, or what? That is psi. Which property I want to know? Momentum, position, angular momentum, energy, that is my operator. These two distinctions you keep in your mind. Okay. Now I am going to use the Qiskit framework to do this. Now I need some tools to run my calculations. The essentials are here. So I'll be using Google Colab. So if someone is, I mean all these, I will write some programs. The files will be shared with you so you can practice later on. Or else if you are comfortable, if you are sitting in anyway in front of your computer, so you can continue doing it, but I will show you by doing some elementary thing and all. So we'll see. So these are the 4 things. I need this Qiskit to enable me to have all these things. Qiskit nature has some extra features that are commonly used for natural system, for molecular problems. Qiskit Air is actually the simulator that we will use. Simulator is what? You can actually have access to real quantum computer where you can run, you prepare your code, transfer it to the machine, the quantum computer, and then they will get executed. But we will not go through that. What we will do is that we will prepare the code, we will put it in a simulator. The simulator works mimicking the quantum computer. Now the 4th line, this pi latex ENC, it gives me some extra features to plot and all. Okay. Now I told you that there are 2 things. One, the wave function psi, the other is the operator. To prepare my wave function psi, I need this something called this quantum circuit that I'll use this quantum circuit. When I build quantum circuit, essentially I am preparing my molecule, I am preparing my system, or preparing the problem that I am trying to say. Then the operators, as in the previous lecture you heard, that the operators that I am going to use are essentially the 3 Pauli operators, x sigma, y, sigma, z, you have seen, the identity operator, and then we can have Hadamard gate, we can have things, the 3 Pauli operators and the identity operator. Combining all of them, I would actually create my operator. I will show you a few example Hamiltonian, how to go about that. Okay. Now, after that, there are 2 more things I would need. I would need this, look at this equation. When the operator A is 1, that means nothing is there in the operator, that becomes, this equation becomes a special equation, that's the probability distribution. So it's just measurement and tell how many, what percentage of your outcomes exist in which of the possible states. As in the previous lecture, you saw that 3 qubit, you have 8 states, 30% in the first state, 20% in the second state, and all these things. So the probability distribution. So to get only the probability distribution, we use the sampler, and to estimate the expectation value, we'll use this estimator. Now I'll go to the my Google Colab. Okay, so I have already, it takes a few seconds, so I have already loaded this. Now I want to this allows me to construct my wave function. Okay, I'll come to that. Okay, let me build a circuit first. Okay, all right. So let me define the name of my circuit. I'm calling it a quantum circuit QC. So I'll do that. I build this circuit. How many qubits I want to build? So it depends on the problem that I am solving. So suppose I said I want to have 2 qubit circuit. So that gave me this. Now I start defining my gates in my circuit. So suppose I want to have first case in the first qubit a Hadamard gate. So I introduce my Hadamard gate and put it in my circuit 0. Now let's see what I have. I can draw this circuit so that it actually we can see. Okay. So now you see I prepared 2 qubits. The qubit 1 is called Q0, the qubit 2 is Q1, and my qubit 1 has this Hadamard gate. Do you remember from the previous lecture? So how do I prepare an entangled state, Bell state? So first Hadamard, then the 0th qubit, and then a C0 gate. So I go back to my this, and I said, okay, I have, this is how put a C0. C0 is a CX. The first qubit gets a control. So, the first qubit gets the control. The second qubit gets the X gate. So that's how it is CX. The 0, 1. So if I decide to make it 1, 0, then you can see that it would go the other way. So it's a C0 where the control is with the second and the NOT gate is on the first. Okay. So when I have this circuit, then I am actually ready to make it in prepare the Bell state. Now, next what? I actually have to do a measurement. So you see, these are all preparing my system, but when I take the measurement, when I ask the question to the computer and it will give me the result is observable. For that I actually need a classical register. The register where the outcomes of the measurement will be given. So I have 2 qubits, so I introduce 2 registers. So that's the place where you see the register get introduced, but now I have to do the measurements. So I do, so I have this QC, the circuit, QC is name of the circuit, and I am measuring this circuit. So I can have the, I am going to follow this way. So I have the first bracket list tells me which qubits information you want, and the second bracket string tells me to which classical register you want. So this simply tells me that my 0th qubit information goes to the 0 classical register, first qubit information goes to my first classical register. So this way I am doing the measurement. So this is how the measurement comes. Okay. Now let us do the these are primitives. Let's get primitives, import now sampler, and from, so sampler does what? Sampler with using samplers I can and estimator helps me in getting the expectation values. Sampler gives me the probability distribution. So these are some of the things that so now I would call my sampler and try to get information out of it. Okay. So I defined so this works in a particular way. So let me define a job which will run my sampler. But it will run on which? The quantum circuit, the name of the circuit I give. So this will give me this. So now the result will be okay. So now print so I have not installed the Qiskit visualizer. Yeah. All right. So I like this prompts of collab. So it helps me go through the programming without remembering many keywords. Okay. So let's see what it has given me. You know which state it is? In the previous class, you saw that this prepares a Bell state. The Bell state is what? An equal mixture of the 0, 0 and 1, 1. So in the ordering, 0, 0 was in the first state and the 1, 1 was the fourth state. So now if you see, it gives me 50% population on state 0, 50% population on state 3. Yes. Yeah. Okay. So that way, if you want any particular change, I can do this. So this is how you actually get to see that the distribution. Now suppose there was another question. So this is how you prepare a Bell state. Now let's see that I don't want a Bell state. Instead, I want the operation of Hadamard gate on each qubit. So now I have 2 Hadamard gates. If I do the sample run, now what did it give? So the first qubit went to superposition, the second qubit went to superposition. Now I have 4 states, all are equally probable. So this way I prepare my system. When I am preparing my system, I am preparing my system with equal distribution of probability to all possible states. If I have 8 qubits, all 2 to the power 8 states will have equal probability. So I am preparing a perfectly balanced superposition state just by putting Hadamard gate in this. Now you might be saying, okay, if I have hundreds of qubits, then if you follow your regular Python programming, you can do a loop, for loop, while and all, just the way you just can construct your circuit in the same way. So I am just showing you the simplest of the versions. So you can continue to increase the number of qubits, add a number of gates. So I can show you the effect of C naught here as well. So it is first Hadamard, then a C naught, then this. I do not know which state it should prepare. Yeah, so this still prepares because the effect of the C naught anyway gets cancelled out because both are always existing in superposition. Okay. Now with this, what have I achieved? Remember this equation? I have only achieved the wave function. I have only created the wave function. Now with this C naught, what have I introduced? A possibility to entangle 2 qubits. One qubit knows what the other qubit is doing. That C naught gate. Based on the state of the first qubit, the second qubit will change its behavior if I have a C naught between them. If I have only one qubit gates, H, X, Y, J, sigma, poly, X, poly, Y, poly, Z, or the Hadamard gate, one qubit will not know what the other qubit is doing, right? So I introduce my entanglement or the correlation between the qubits by introducing this. Now imagine you have a molecular system. You have 2 electrons, they are always aware of each other. In quantum mechanics, you have this Fermi hole, you have this Fermi heaps, telling that if an electron is present here, the probability of the other electron at this position is high or low depending on their spin, right? The famous Fermi heap or the Fermi hole thing comes. So every electron is aware of the other electrons. So they represent a system where they are correlated. That correlation is beautifully captured by this circuit construction. I am now preparing a wave function which is where each particle is connected to the other particle. Now the next step is that I prepare my, so first equation, up to now what I have done, I prepared my psi, I got the overlap function. So I have shown how to get this, I have shown how to get this, right? This is just the quantum circuit, this is the sampler, this is what I did. Now I am coming to this. So what I would do is that I will prepare the operator and do the measurement afterwards. So then that will give me the expectation value of that. So let's build the operator. Now the operator, so let's define something called an operator. To get these operators, you know, so I'll be using Pauli operators. I'll see how many qubits I have. I still have 2 qubits, so that's a. So I have Pauli operator. I can have. I prepared this place for 2 lists. The first list is now the nature of the operator. I can have, let's say this is a 2 qubit problem, right? So the operator must satisfy the same state. So the first list is, suppose I have Ix, that's, so my operator in the first qubit is unitary and the second qubit it is X, and this is the coefficient of that operator. I have not from Qiskit quantum info. No. So I can print my operator. So this, I can zoom in the screen. So this simply tells that this is my Ix operator with this coefficient. I can keep on, so I can add another operator. So suppose I have Xi and this operator has a coefficient of 0.5. So the operator that I constructed is Ix plus Xi. So the total operator is 1 Ix plus 0.5 Xi. That's my operator. That's the question that I am asking from the system which is defined in the quantum circuit. The quantum circuit defined my wave function psi. I will also call in some time the same thing as ansatz, and the operator is what I am preparing. The operator asks the question. If I am talking about an Ising model, I will have a different operator. If I am talking about a hydrogen molecule, I will have a hydrogen molecule Hamiltonian. That operator will be different. If I have a benzene molecule, I will have a benzene molecule Hamiltonian. That will be a different operator. So the operator is, again, what question am I asking for from the system? Okay. I can also operator show that in a matrix format. So you see, this is Ix plus Xi. So maybe I make it only Ix so that you understand it better. So you have Ix. This is how it would come. The direct product. So the first qubit has I. So 1, 1 in the diagonal. The second has X. So the product will come out this way. So someone was asking which book to follow. Professor Majumdar said the first book, take it from me, the best way to learn is that book. First few times you do the multiplications by hand just to make sure that you know, and then get started with the way and go through all the problems that are given in that book just by doing the coding and verifying the answer. Just by going through all these problems, you would be actually introduced to many tricks as to when you are building a circuit, when you are building translating a quantum mechanical problem to the qubit language, many of these the problems that you solve will help you immensely in formulating those problems. So that would be the best way to go about learning. Okay. Now I define my operator. Now what is the next step? I have to now estimate, get the expectation value. That's the third step. So now I define my estimator, which is, I I define this, and then I define a job that now when I run this estimator, what do you think it would want to know before it can do? It would first ask me, well, you want to get the expectation value, give me the wave function, right? I'll call that quantum circuit, that's my wave function. Then only with that it will work? No, I needed the definition of A. So it will say give me the operator. So both the things I have to give. So I have to give QC, the quantum circuit, and my operator. But that will be an issue. So let me tell you one thing. What has happened here, I have defined my quantum circuit QC up here, but I have made a measurement, right? I built that circuit, but I have made the measurement. In the last class, what did you see here? That when I make a measurement, I collapse. So my circuit, I have to rebuild it, right? The no cloning theorem in action in some way, yeah? So I need to build that one more time. So I just redo this without the measurement. So then my QC gets defined. I hope this works. All right. So let me put my result in a no. So I don't. So here this won't be useful. Or I actually need okay, it was giving me okay. What did I do? Okay. Yeah, so values. Okay, so this gives me, when I was, look at the difference in that result that I am getting. When I was doing a sampler, I am calculating the distribution. I have 8 states, I have 10% probability of going into the first state, 10% in second, all this. So I get a distribution. Now what am I doing? I am measuring the expectation value. The wave function psi can exist in a superposition of state. This can, this is essentially same. When I am making the measurement, this is an integral. So when I do the integration, or in a matrix formulation, I multiply the vector with the matrix, then what I get? I get a single value. The expectation value, the outcome of the experiment, the measurement outcome, that's a single value. It just turns out the value is 0. Right? So when I calculate the expectation value, I am getting the expectation value as 0. This may, so from your quantum mechanics, you know that if the psi is not an eigenfunction, you would of course, when you do the measurement, you will have multiple possibility that it can get into, it can collapse into, but when you make the overall measurement and get the expectation value, you will get some average value. The average value need not be an eigenvalue of the system, right? It can be any value based on the individual states that we have. So now what I have achieved? I have achieved the first step, prepared the wave function. How did I do that? By defining my quantum circuit. The second step, I calculated the distribution using the sampler. The third is I could get my expectation value using the estimator. The result, the values, even if I don't give, it actually gives the same thing, but with some other things. So there are, so this has other information. So the way I am doing is that there are many more things that are possible here. Some of which I know, many of them I do not know myself. So I am keep sticking to those things that are essential to get you started, to get a feeling how to do it. I assume that at least 10 or 20% of the audience end up doing it. I'm sure in a year from now, when we meet, if we meet, you will teach me more than what I would have known then. So that's the idea. I'm getting you started, but if you are interested, you will explore it further. Okay, so this is my story. Now, all right, so it's very simple. Exactly this, I think Arindam, who was asking, all these things are very easy to do, but what did we gain? Now the question is that if I know my wave function, I know my operator, everything I know, I just did the expectation value, just the measurement. Now thing is that what am I often interested? I want to have the system where the operator S eigenfunctions I do not know. I cannot solve the Schrodinger equation corresponding to that. Then I want to have some way of getting the wave function, getting the eigenfunction of A without actually solving it exactly. One of these approaches is called the variational theorem, which which is what we are going to do that, but let me come back, do the same step, expectation value determination, but for a realistic system. Let's simulate nature. But then I can go as far as like a spherical chicken kept under vacuum, right? That's my reach to the nature. So the system that I want to deal with is Ising chain. So what is that? That imagine I have many spin centers arranged next to each other. Each electron, so that's the spin center you got introduced. If you have two spin centers, you know that they would couple with each other. If you have four, one, you can imagine the nearest neighbor coupling. So one will interact with two, two will interact with one as well as three, three will interact with two and four, and so because they are in a chain. You can extrapolate that to a square lattice, you can do a 3D lattice. So this is in general applicable to all the lattice models that we will do. But we will pick up the simplest of the case where I have this problem. My if I use this, everybody can see. So these are my spin centers aligned nicely. They will interact with each other with a neighboring interaction. And then I am actually applying a transverse field. So these interactions are happening in the z direction with each other, and I am applying an external magnetic field along the x direction. Now when external magnetic field comes, each spin center will interact with that external magnetic field while simultaneously interacting with its neighbor. So these are the two terms. The first term tells me that the two particles are interacting with each other. I will introduce the nearest neighbor introduction here. And the second tells that each particle, each spin is now interacting with the external magnetic field that is being applied here along x direction. So the Hamiltonian that I would write down is my, the first term will have the sz term of I and I plus 1, and the second term will be Sx. So this is essentially, since I am talking about the spin centers, so directly I am translating my operator to spin, polyspin to polyspin operator. So therefore, with poly operators, this Hamiltonian looks like this, the second line. So where my Zi and Zz are the two poly Zs in ith qubit and with the jth qubit, ith spin center and jth spin center, and this xi is ith spin center's interaction with the external field, right? So now, how do I prepare my Hamiltonian? Let's build that and then come back here. Okay, so I am trying to do Ising chain. That's the goal here. Now I will define my Hamiltonian. Hamiltonian will be defined by the Pauli operators. I know that I can have two strings. One string is to define the operator, the second string is to give their coefficient. The first string, in the first string, I can introduce, so I'll do it with two spin centers. The first one with ZZ, that means first one is Z, second one is Z. So Zi, Zz. So one is interacting with two, that one. So what would be the strength of that coupling? Magnitude of that coupling? J, right? So let me introduce something like, instead of calling it let's say I'm giving a value j, and then I will also introduce a transverse field coupling. So I'll have one parameter so that it is easy to, so G coupling and J coupling. J coupling is with the nearest neighbor, G is with the external field. So I'm defining G coupling as some fraction of the J coupling. Okay. So now you tell me, so this gives me the J coupling. So what should be its coefficient? J coupling. So what would be the second term? Now my spin center 1 will interact with the X field. So I will have, let's say, a term Ix and a third term Xi, and both of them will get the coupling, G coupling. Alright. So I prepared my Ising Hamiltonian, so I can print the operator because this is print. So this is what I have got based on the value that I have put in the coupling. I can also write that in the matrix form. Now classically, if I want to solve, I mean in a classical computer, what would I do? I will take this matrix, that's the Hamiltonian matrix, diagonalize it, the eigenvalue is, yeah, the eigenvalue is the energy. Huh? Okay, minus j, so j because of the sign, fine. Because I wrote minus j. Yes, so that's an overall factor, you can do minus 1. So it's ferromagnetic coupling or antiferromagnetic coupling, so j is magnitude. Okay. Okay. Which part exactly you want? Okay. This one. The entire collab page, whatever I am working with, I will share it with everybody. Fine. So how would I solve this? I would just diagonalize it. Now very easy, 4 by 4, so I can do it very easily. Now if I have 10 cubic centers, spin centers, what will be the dimension of this matrix? 1000 by 1000. I still can diagonalize it. If I have 40 centers, 40, that becomes 2 to the power 40, which is gigabyte. So 10 to the power 12, 10 to the power 12 matrix with only 40 centers. If I have 60 centers, forget it, right? Very quickly the problem goes out of hand. But when you think about quantum nature, if I have 100 qubits, I can prepare my 100 spin center exactly and get its true energy, quote and unquote true energy, because you will see how I am getting the true energy. By doing a measurement, it's like preparing a system and getting extracting the information out of it. Okay, so this is my Hamiltonian. Now the thing is, I'll have to, if I take the expectation value of this, I'll get an energy. The thing is that that energy will depend on the nature of the wave function that I have prepared. So this is where the variational algorithm comes. So you have used we have studied this variational theorem. So the first step is prepare the trial solution psi theta, where I will introduce you to theta, then measure the expectation value. You already know how you can do it. And then the third is that this psi is defined in terms of a theta. If I change my theta, then psi of theta changes. Naturally, the expectation value also changes. Now the question is that find those set of theta that will minimize this energy. That's the way variational principle works. You start with a trial function, give some flexible parameter in the trial function, change the parameter in the trial function until the energy is the lowest minimum possible, and that set of parameters give you the true solution within variational principle. Okay. Now on a quantum computer, how do I do? This is where I define the so-called ansatz. How I prepare my initial state. So far all this qubit thing was elementary, that I'm being constantly reminded of that question that the student asked. so far. Now I am introducing an ansatz which is more representative. I would show you a few examples how it. So to prepare an ansatz, I can have multiple different schemes or ideas. So I am going to use these two local ansatz. Ansatz means what? If you have done your variational principle calculations, you would actually be starting with a trial function. Now suppose you are solving, I don't know, a hydrogen atom problem. I know it is a true solution is an exponential function. The ground state of hydrogen function is e to the power something. Now if I start with e to some exponential function with the exponent not known, variational principle can give me quickly the true solution. But you imagine, instead of starting from an exponential function or a Gaussian function, if I start with a function which is completely crazy, I just start with a function which is quadratic, y equals x square. That's unlikely to give me a result. What is the difference? The difference in the first case, I know I am starting from a reasonable guess for my trial function. In the second case, I am horribly wrong. If I start with a trial function which is horribly wrong, I shouldn't expect a great result out of it. I mean, you cannot minimize, you cannot beat a dead horse and make it move, right? So the answers preparation lies, that's where the information, the knowledge about the problem that you are dealing. A chemist will bring chemical information, a physicist will bring the physics information to the problem, any other field working material science will bring those information. That's where the answers preparation would work. But in any case, in a general way, the answers will have such parameters. What is that? How many qubits you are dealing with your system? 4, 5, 6. Now, the rotation blocks. The answers, these rotation blocks allow you the free parameters, how many parameters you are joining. Then the entanglement blocks, so one qubit getting entangled with other. So we can use the Cx as a block. And entanglement can be either linear, that means if I have 4 qubits, 0 with 1, 1 with 2, 2 with 3, 3 with 4. Or full, 0 with 1, 1 with 2, 2, 3, 3, 4. And 0 with 2, 0 with 3, 0 with 4. Each qubit is entangled with others. Now, this is the first example is a case where I have, can you tell me, where is the rotation blocks coming? The red ones are Rx, the blue ones are Rz. These are rotation operator. Rx is e to the power ix by theta, right? That's the rotation operator. Rotation operator takes the angular momentum in the exponent. The Cx is the entangler. So you see, is this a linear or a full entanglement? It's a linear because 0 with 1, 1 with 2, 2 with 3, right? Now I can show you another. What did I change? Can you tell me? In my code here, both are 4 qubits. I changed the pattern of entanglement. So now here 0 with 1, 0 with 2, 1 with 2 and all these entanglements are there. In both the cases, how many thetas are there? Each Rx is a rotation gate. But rotation by how much angle? That is up to you. So that's a parameter. That's a free parameter that I have to optimize. So in the first case, how many? If I say there are 16 parameters, each R block will have a parameter, how much you should rotate. So how many parameters you have? 16. The second case, you again have 16. Then the next feature of this is how many times you repeat. You can actually take this and this is being repeated. The first one is being repeated here. How many times? 3 times. This is repetition 3. What do I get here? Here I have actually 32 parameters over here. This sentence is very useful here. This was an exchange between von Neumann and Fermi. Von Neumann criticized Fermi's approach, saying that if you give me 4 parameters, I can fit it to an elephant, and if you give me 5, I can make him wiggle his trunk. The idea is that what it gives me, if I have more parameters that I can manage with, I can have more flexibility and I can converge to a true solution or the minimum solution in a much more effective way. So more the number of parameters, more is the likely that I will hit the lowest energy solution. But then the problem is that more is the parameter, more number of optimizations I have to do, right? So there is always a cost versus efficiency problem comes out. So this kind of answers we will prepare now on our circuit. So now the next step is my answers preparation. So I'll see if I can get these. I couldn't copy them over here. No. From okay, circuit library. So this 2 local is the name of the answers that I am doing. So now I am defining my answers as 2 local. Now naturally what all will it will first require? It will require my number of qubits. I give that as num qubits. Let's say I give it 2. That's because I am preparing a 2 spin center change. Then next thing is that rotation blocks. So again I would have Rx, Rz's. Now what rotation blocks do? They introduce number of free parameters, right? Now I need entanglement blocks because it's not enough to just rotate them. I also need entanglement. So I do that with the Cx. Then what else? Entanglement nature, whether I want it in linear, I want it in full, here I do. Then next what do we? If I want to have more flexibility, I will repeat them so that I have more number of free parameters. So I have repetition equals 1. So this prepares my answers. So I can answer, so it's just like a QC. So the same thing that I did earlier, I can draw these answers. So these answers has how many parameters? Okay, so but this doesn't give me lot of information. What I'll do is that I'll ask it to decompose and show me. So I have earlier case I had 4 qubits. So this is a 2 qubit problem. So 2 qubit, how many parameters I have? 8. So now I am doing a variational calculation with the parameter these 8 parameters. So initially, so I can define. So let's say I define an array param values. Let's say I will do it all 0. So I multiply with the length of the answers. Answers parameters. So what it does, I'll print. So what it does is that I am initializing the initial thetas. So here I have given all thetas as 0, right? So I am making up my mind psi nature, whether it's an exponential function or a quadratic function. How did I define that? Whether I am taking an entangler or a Rx Ry or Rx Rz, number of repeats, all these things constitute the nature of the function. The values, psi is function of alpha, the free parameter, the theta is what I am giving it with the param values. But if I give a set of param values and calculate the expectation value, that will give me the energy or the expectation value at that set of parameters. That is not optimized, that's my initial guess. Now I have to find out how I optimize this to get my things going. So I can either have any non-zero value as well, or I can have a random distribution. All these things you can do. Now next thing is that I have to provide it to an eigensolver which follows this variational principle. Now I'll take you to this picture that you have already seen before. In this picture, this is my wave function psi in. How did I prepare that? That is my initial state 0 0 0, or I want to make a superposition of all, then each qubit I will put a Hadamard gate so that all 8 states are equally probable, and then I am introducing my answers, the circuit structure I get. Together, Now I prepared my wave function. This is my trial function psi theta I. And this is my operator. In this case, what is the operator? The Ising model, the Hamiltonian of the Ising model. Now I will make this measurement. This measurement is quantum computing measurement, right? Because I am preparing a 100 qubits problem. That means I have 2 to the power 100 number of states. Now when I make a measurement, the expectation that would come out will know about all the 2 to the power 100 states and give me that energy, right? So that is quantum heavy. So I will do that on a quantum computer. Now I got my thetas. I have initial set of thetas. After the measurement, I will pass this information to a classical machine, because the classical machine I am very used to. What the classical machine will do is that it will change the theta values in a certain directional manner using different algorithms. It can do a conjugate gradient, it can have many other optimizer techniques that it will follow. But that process will happen on the classical machine. The classical machine will give me the new set of thetas that would have lowered the energy, and then with that, those new set of thetas, I will reconstruct my answers and prepare my new function and do a measurement. That energy will be lower than the previous step, and I will continue to do until my energy doesn't change anymore, right? So that's my variational problem. And I do that by using a VQE solver. So I would get this VQE from Qiskit algorithms, this, and then I will also need to define an optimizer that would do. Okay. So I have, let me import that from Qiskit algorithms. Import VQE, that should work. And from, it's not enough to have only the VQE algorithms. I also want, what is that name? I want an optimizer. Optimizers, import. So it is asking me to take SPSS. So there are many possibilities. We have benchmarked in a work different optimizers and their role. So now I am done. So here I am defining a job VQE as VQE it calls. Now imagine, now you think what it needs. First thing is that it has to optimize the thing. So first case it would need to know that what is the expectation value. So for VQE it needs expectation value of this. So it would first ask for the estimator. So my estimator is already done. And then it will ask me for the answers. Then it will ask me for the optimizer name, and I can have these multiple options, how many steps it should do. Suppose you are entering a system where it is very hard to optimize, you may need larger values. So this gave me this, but now I have to run VQE. Okay, so VQE has now what am I asking? That alright, VQE, the eigensolver. Now you have already taken the information, what is my answers, what is my estimator. Now you compute the minimum eigenvalue, because minimum eigenvalue means I am minimizing the lowest energy of my operator, the Hamiltonian. I don't know how I defined my Hamiltonian here. I have told it is H. So now it is doing this, and then I print result or results. Huh? What would, I think, all right. So what it did is that now it optimized. So the lowest solution that it has found is given here. Eigenvalues is 1.0818. What were you expecting? What did I have the system? I had the system of two spin centers. They are still coupling with an external magnetic field because I have given a non-zero value of G coupling. So that brings this value. Now you see the optimized parameters, the thetas are over here. So these are my final set of optimized parameters that it has done. Now suppose, so if I had with these parameters, if suppose I initialized this, let me create another. Okay. Now you see, what I did is, you should be able to identify this, I just quickly did it. What does it do? Given a parameter set, it just I asked it to give me the expectation value. So I defined the answers, the Hamiltonian, the parameter values are initial parameters, whatever I have given, and print the result. If I had gone ahead with this set of parameters, my energy would have been, the energy would have been 0.97. Is it the true energy? No, because that was, how is it coming? Because I have given it some random value of theta. Then the energy is there. Now I am asking the program, okay, minimize the energy by changing the thetas. Now you see that if I just make it 0, all the parameters 0, and rerun this, it will give me a different value. If I give all 0.2, and it will give me if I keep on changing my thetas, that means the parameters, I am getting a different value. Now what I would do, I would take these values that VQE gave me after solving it, and I will put that here. I will define this as param values equals this array. Now you see these 8 parameters are given here. Now I estimate it. Of course, I get the same energy that I would have got here, right? What does that mean? That means that if you give me the true wave function, I can give you the true energy. The question is that you don't know the true wave function. The VQE or the variational way of solving is that you have free parameters, you optimize the free parameters so as to minimize the energy. Now this is for a lattice model. You have chains, you have certain interaction, you complicate your Hamiltonian, you have a 2D lattice with all interactions, you will construct a separate Hamiltonian, but the process is same. If you have large number of qubits, you can do many things, right? But the process is same. All right. Now what we would do is we would go, no, I did not want that. Okay. Now what I would do, how much time I am already, Sandeep, how am I? 103. When did I start?
Hey, you can go for 10-15 minutes maybe.
10-15 minutes.
10-15 minutes. Yeah.
All right. Fine. Now I am coming to a molecular case. But the thing is that what I have done is that I have introduced you to most of the steps in a calculation. Only thing is, in a molecule case, there are a few other nomenclature based issues that will come to. Otherwise, the variational algorithm, preparation of the answers and all these things are already, I hope you have understood. Now when I come to molecular case, first step is that I write down the molecular Hamiltonian. The first line that you see in this equation over here, the Hamiltonian H, this small Hamiltonian has The first term, so there are 1 electron operators, there are 2 electron operators. What is a Hamiltonian? Hamiltonian is an operator that will give rise to the energy of the system. If let's suppose hydrogen atom, I have a nucleus, I have an electron. So electron will have kinetic energy, nucleus will have kinetic energy, but nucleus is too heavy, so I will ignore its kinetic energy, I will make it 0. So only electron's kinetic energy, but electron will also interact with the nucleus through Coulombic interaction. So all these interactions, I club them together and call it a Hamiltonian. If I have 2 electrons, the 2 electrons will repel each other because they are of the same charges, so they will also have a Coulombic interaction. If I have 100 electrons, each electron will couple with every other electron, so that's the requirement of many qubits problem. So in that way, I can write down my Hamiltonian. This is. Now the thing is that the molecular system or the electrons are indistinguishable in a molecule. Like if you have water, 10 electrons, you can't distinguish electron number 1 from electron number 3. They are all the same, right? Once they have formed the part of the molecule. Because they are indistinguishable and also because the fact they are fermions, that means they carry half integer spin half, they have to satisfy some special rule. They have to be anti-symmetric with respect to exchange. So that means any 2 electron, if you exchange, the wave function, the psi that we prepare must change its sign, must become negative of itself. So that's a requirement from principle that we cannot violate. So the wave in the Hamiltonian, if this is the Hamiltonian, the wave function that we get is written down in the so-called Slater determinant. The Slater determinant knows already how to prepare an anti-symmetric wave function for a many electron system. Those of you who do not know, excuse me, take it from me. Now the thing is that those of you know, the next comes to next step. Okay, fine. How do I translate it to the quantum computer qubit? I see electrons and qubits, but where is the connection? The connection becomes easier when we rewrite the Hamiltonian in a different language. That language is from first quantization, that's in the title, to second quantization. The first quantization makes the Hamiltonian, expects the wave function to be anti-symmetric with respect to exchange. In the second quantization, the wave function's role has been dropped. Wave function doesn't have to follow all these strict rules. The Hamiltonian itself is trained to have those operators which follow anti-symmetric by definition. The conversion of first to second quantization, if you are interested in the molecular application of quantum computing, you must do this and get yourself used to it. Now, what happens is the second quantization, this is the second line. This gives you the ladder operators, the creation and the annihilation operators, a dagger. Then what happens to the wave function? In second quantization, the wave function follow a very simple rule. These are just occupation numbers. If an orbital has an electron, then the occupation number is 1. If it doesn't have, it is 0. Consider hydrogen molecule. This is my hydrogen molecule. I have 2 hydrogen atoms. Each hydrogen atom has 1 electron in a 1s orbital. When I form one hydrogen molecule, I essentially have 2 orbitals. In these 2 orbitals, I can accommodate maximum 4 electrons. Each orbital can have 2 electrons, one upspin, another downspin. Upspin and downspin are in this representation has been written in green and blue bars. These are the boxes where the electrons can be filled. Electrons are indistinguishable, they are yellow balls. They can occupy wherever and depending on this. So what is the occupation number of this representation? 0, this is called 0, this is 1, this is 2, 3. So this is 1 in 0, another is in 2. Right. So if I have to give this occupation number, so this becomes 1, 0, 1, 0, 1, 0, 1, 0. Right. Now, I will show you the link between the molecular Hamiltonian and the qubit. This is in the fermionic space, that means Hamiltonian. So this is, I have 2 1s electrons in the ground state. So what is the occupation number? 1, 0, 1, 0, 1, 0. Third one 1, 0. That's how it is. If I remember, the qubit can exist in 0 state or 1 state. So there is a parallel here. So the electron, the spin orbital here can either have a 0 electron or have 1 electron. The qubit can either be in 0 state or 1 state. Now you see that the electrons in a molecule can be mapped to qubit in a quantum computer. right? Because the parallelance is there, and that comes beautifully comes out when you write the Hamiltonian in second quantization. But the trouble is this occupation of the electrons, they are fermionics. The qubits, they follow the Pauli spins, so they don't have this thing of antisymmetric with respect to exchange. So then what we need is a mapping that ensures the antisymmetric nature of the wave function. What it does is that it, instead of this operator, you saw this operator in the Hamiltonian, this is now mapped into the Pauli x, Pauli y, and these terms, they ensure that any two qubits are exchanged, the wave function becomes negative of itself, antisymmetric with respect to. So this is the mapping. So now for the quantum molecular system, there are 3 steps. The step number 1 is write down the Hamiltonian in first quantization. Then I said its parallel is not clear, so go to the second quantization. In the after reaching second quantization, I see that it's not enough because I have to translate it to really, like first quantization, I don't see the parallel between molecule and quantum computer. In the second quantization, I start seeing that there is a correspondence. Then I need a mapping. The mapping takes me from fermionic space to a qubit space. That mapping is called Jordan-Wigner mapping. There are other mappings, Brabby-Kitaev and all other things. So they are matter of details. So once I finish these 3 steps, any molecular Hamiltonian is now expressed in terms of what? The Pauli gates. Just the way I did 2 spin chain Ising model, I can now do hydrogen molecule which has 2 electrons in a 2 qubit, or I mean the minimal way, right? If I have more qubit, I can have more excitations and so on. So the parallel is there. So now what would I do? I now know for a molecular case how do I construct a Hamiltonian. If I know how to construct a Hamiltonian, I can map it to a qubit space. My qubit Hamiltonian is ready. How do I prepare a wave function? Through an ansatz, 2 local answers. It is general in nature. I can use it for any problem, even for molecular case. What does ansatz give? It just gives me 4 parameters to which I can using which I can fit an elephant. For Neumann, thanks. Right. So my elephant, it so happens, is the hydrogen molecule. If my elephant is lithium hydride, then also my 4 parameters will be able to do it. My ansatz doesn't have to know about all these things. It's just 4 parameters that can fit to elephant or to a giraffe or to a tiger, whatever you give me. Right. Ansatz gives me the opportunity to optimize. The Hamiltonian gives me the information about the system, and variational principle is there to help me out get the lower energy solution. Now what I would do, I would take you through a code without writing them. You already saw that I am slow in doing this. So I have, this is for molecular case. Again, I need some more toolkits. So PySCF is a Python based program using which you can actually solve Hartree-Fock and post-Hartree-Fock methods. So it is using to get some integrals from there. So I have already run this, it takes a few minutes. Now the second step is molecular geometry, where my atoms are. So this comes from the PySCF driver. Now here you see, those of you who are introduced to quantum chemistry, you would know this is called the Z matrix. This simply tells in a molecule which atom is where. Water, you first fix 1 oxygen, the second the hydrogen is 1 angstrom away from this. The second hydrogen is over here. So give its Cartesian coordinate so that the bond distance angles are defined. So the molecular architecture is prepared. That is your job, because you define your molecule. What do you want? A water molecule, 2 water molecules, 100 water molecules, a protein, whatever you want, you give it over here. Now, so that becomes the, then you, I mean, this step is not necessary for a quantum computing, but then we are actually doing it so that I can show you something. Now I am doing it for hydrogen molecule. I am writing down number of particles. How many particles I have? I have 2 particles. That means 2 electrons. 1, 1. Why is it written? Because I have 1 alpha electron, another beta electron. That represents a singlet ground state. If I want to have it in a triplet state, I'll have both in alpha. So suppose I have a triplet state. That means I will put both the electrons in alpha part, ground and first. So my occupation number vector will become 1 1 0 0, the triplet state, and I can prepare other states. Now number of spin orbitals is 4. Why 4? Because I have 2 hydrogen, 1s, they come, 2 orbitals, will form 2 molecular orbitals, each can have 2 electrons, so that means 4 spin orbitals, 2 into number of molecular orbitals. So I have now 2 electrons in 4 spin orbitals. So the number of spin orbitals define the dimension of my qubit space. Now this is the next step, is that I created so far I created my Hamiltonian in the first quantization. We normally do. Now the second thing is that I have to transform it to the second quantization. In the second quantization, this is how the Hamiltonian looks like. Now I just had taken a screenshot of it. So this is creation with respect to the zeroth, creation with respect to zeroth, annihilation, and these are its coefficients. So these are the operators, individual terms, these are the coefficients. But are you able to read them in the quantum computer yet? No, because this is now in the second quantization form. Now I have to go to the third form. The third step takes me to the next place, is where I am doing a Jordan-Wigner mapper. So I define my Hamiltonian, ask it to convert it to a second quantization form, then use a mapper, Jordan-Wigner mapper in this case, and then I do a Hamiltonian operator. Now you see the print Hamiltonian operator. So this is hydrogen molecules Hamiltonian in qubit space. Do you recognize them? I. So can you tell me this term, what is that? Let's Z triple I, so that means I have 4 qubits. The first qubit has a Z, second, third and fourth have nothing, that's yi. So this will give me, so now let's talk about this. This is XX, Y, the first X, second X, Y. Now my Hamiltonian, molecular Hamiltonian has been converted to this X, I, Y, Z. Now I know if I have, like I solved it for Ising model, if I have one Hamiltonian ZZ plus IX plus XI, I got that energy. Now I have this. Now what is the task? After I finish this journey, now next is come back to this, get the expectation value by fitting some parameters. You prepare your answers, fit that parameter and do that. So this is what we are going to do next quickly. So this is repulsion energy, because the nuclear repulsion energy, that's a constant I can always add. I'm sorry, I'm rushing a bit. And now I have used a 2 local answers to prepare my wave function. Just the way I did that, but okay, it's running. Okay, it's installing this PyLatex also, that's why it is taking time. So again, so I have, you already know this, you are familiar, we did it for Ising model. For hydrogen also it works the same. Somnath, I need, okay. Now, this step does what? It estimates, calculates the expectation value, but taking which parameter? Initial parameter, that's not enough, right? I have to optimize them. Now this is the next step that it does, that it optimizes the process and, okay. I will share this file, but then I think the process is same, so it becomes. Now what you see here, that when I started with my initial set of parameters, the energy that it came out to be this value, right? As it progresses, the optimization of parameters, thetas are learning, they are getting better and better and better, and then you see after 100 steps, they are not changing, so I'm satisfied. But luckily in this case what happens, I can solve this also exactly, because it's not a big problem. So in this case I am exactly in a classical computer I am doing it, and now I am plotting the comparison of the orange line is the exact solution on a classical computer. The blue one is quantum computer through a variational approach, how it is approaching the true solution step by step. In these cases, I see that it goes and it goes to a true solution because I know the true solution. From these kind of calculations, I get the confidence that for those problems which I cannot solve in through classical machine, then also I would have reasonable chance of going to the true solution, because this is essentially an optimization problem. Okay. Now you see, it is taking a lot of, many steps and is still not doing very good. That's where I would stop with the next step. The thing is that this is, I'm using a two local answers. This is a general answer, preparing the wave function, which works for all problems, but it doesn't have the flavor of chemistry. With hundreds of years in research in quantum chemistry, we have accumulated a lot of information, lot of knowledge. Now, can we have a chemistry-inspired answers that already knows a lot about the system to help us arrive at, it's an optimization problem. Optimization problem, if suppose you are in a place which you are completely unaware of, you are trying to find something, it will take a much longer time. If someone else comes, like you are from IIT Kharagpur, from chemistry department to come to this, if you know, you will immediately come. That information that you already have will help you navigate the path easily. That's where new answers creation is important. Modern research, let's say in any field, you will do that. You prepare new answers so that the calculation becomes faster, more reliable, and this is what we have done. The one answers that we are using here is UCC. It is based on couple cluster theory. So I really don't have time, but I'll just show you the beautiful result over here. Note the difference. So here I'm exactly taking the same Hamiltonian. What I changed is the nature of psi. Remember that example, instead of an exponential function, if I take a quadratic function, what happens? So here I am just taking a chemistry inspired wave function, the entanglement, rotation blocks and all. And you see in 40, 50 iterations, I am there and I am doing good, right? So this is where I stop, that once I introduce subject domain, subject knowledge to quantum computing, then I improve my performance. So quantum computer also needs help in depending on the problem we are doing. We managed to do it for hydrogen H2 molecule, but let's say up to 20 qubits or so we can do, we have done on several things. So that's where I end. The codes will be available to you based on your interest, based on your thing. You can keep changing your system, Hamiltonian, answers, and do this. All right, so that's where I end. Thank you very much.
Professors are here, and if you have questions both for online and I think the online cannot hear me. You can hear.
Yeah, so if I can tell, if there are any questions, please ask now. We can take a few quick questions, and if you still have more, then we can do it later through emails and all. Anyone from online? Somnath, if you can hear, he's not there. If anyone wants to ask, switch on the audio and then ask. Acha, they cannot unmute. Acha. Until then, we can take question from here.
How really we can get inspiration to make a specific answer to a specific problem?
For example, the way what couple cluster does is that we have this formalism that's saying that the true energy of a system comes out if you is some linear combination of all possible electron configurations. When in hydrogen molecule, for example, the 2 electrons, I kept them in the lowest orbital. I can prepare another state by keeping the 1 electron in the second orbital, higher orbital, or I can keep both in the second. That will have higher energy. Now the true solution of this is some linear combination of the 3 states, where the lowest energy would have maximum contribution from the first configuration. So this is what is called configurations. Now in chemistry we have multiple configurations, and introducing interaction between those configuration enhances the electron correlation. That's how we have solved. So what UCC does that, it starts from a Hartree-Fock answers and builds in single excitation, double excitation, and we also know that single excitation will have this kind of contribution, double excitations will have this kind of contribution, and that's how the rotations, the excitations, they are controlled in those cases. Yeah. Can you use the topics for research? Thanks a lot. Yes, research purpose. Actually, we are doing on a very similar. This is often the starting point of our research. Any PhD student joining would go through these exercises in first month perhaps, and then start building and looking at what are the avenues to do further improvements. We are kind of exclusively working on the variational VQE based approaches. We can now look at how to calculate the excited states. One thing I did not discuss at all is that how do I do time evolution, right? So all these are research problems. Okay, I can hijack the platform to announce. So we are also looking for PhD students interested to work in this field together with joint supervision between me and Sonjoy Majumdar. So if you are interested, do let us know. The advertisement ends. Okay. Any other question? Okay. All right. Okay. As I promised, I'll share the Google Colab files with everybody. Postdoc? Yeah, we'll be very happy, but only thing is that with the postdoc we have limited funding opportunities. If you are interested, get in touch. We can find an external funding source and we would be more than happy. Yeah, IIT also offers postdocs. So yes, there are. Please get in touch. Yes, yeah. So there is machine learning approach, how to do that. There is quantum Monte Carlo. So yes, all the fields that you think exist can be coupled there. Yeah. So this is a thriving field. So you can learn from other fields and come back and apply it here.
Procedure, if you see population, there is machine learning.
Yes, we have, we work also a lot with our UG students, master's project, BTech projects. But if you are outside IIT Kharagpur, we may or may not have an official way of doing it, but then you get in touch again. Yeah, summer internship is certainly possible.
He is inside or in the model.
He is inside. Oh, yeah, sure, please meet us. Sufficient quantum infrastructure for the implementation. So at the moment, what is happening is that we are mostly dealing with simulators. The premise is that okay, once you take these and apply them on quantum computers, one thing that is unexpected or that is going to be a big surprise is that noise. Right? You remember I told you that the classical bit is like a switch, either it's on or off. Right? Quantum qubit is anything in between plus the two end states. Now what happens is that this decoherence, when I expected my camera to be on, it is off, or when I expected my camera to be off, then it is on. That's the problem. When I expect my qubit state to be at 0 because of the operation, I should get 0. But the noise takes from 0 to 1. So now you know if my camera was supposed to be off and it is on, then there is trouble. So that noise creates the most trouble. Now what we do is that in our simulator we build in noise. So we use the real quantum computer data. So when they run the computer, it generates a noise. Those noise library we incorporate in our model to test and learn how we can improve despite the noise. That's what we do. So at the moment we are really not all the time running on the quantum computers, but time to time we do submit some small jobs to check them. Oh, that you please ask the organizers for about the certificate. So they would be able to answer you. Yes, there will be a certificate as I am being told. Anyway, bring more questions, else we have exactly 1 minute to end. So where lies the difficulty? Now, for example, if I go 100 qubit, so all those nice things I told you at the beginning, I'll start negating myself because that's what the reality is. So now you see I'm doing it on a simulator. The simulator is also performing something. It's mimicking the result of a quantum computer, but it still is limited running on a classical machine. Right. So I can design a circuit 100 qubit, but when it does, the simulator does this operation, sampler or estimator, then it runs into problem because it is limited by the number of classical bits available to it. So I can build the circuit 100 qubit with a for loop. For I go 1 to 1000 build Hadamard gates and done. But then after that, when I do sampling, it has to deal with 2 to the power 1000 states. How will you do that on a classical computer? So that will not work. So I have to put it on a quantum computer for those problems. And when I put that on a quantum computer, I need to have that access, long time access, noise resistance. So this is where we are doing. So now what is the research that we are doing is that develop new methods, develop new capabilities to do the calculations on a quantum computer, which will come hopefully in near future, which will be fault tolerant, or they will have error correction, error mitigation techniques inbuilt in them, then we'll be ready. So we are developing, we are learning from small systems, what mistakes we are doing, how I can correct our errors, how we can minimize, how to map a particular problem. You see, this Hamiltonian mapping that had to be done. Now once I am able to do it for 2 electron Hamiltonian, I can do it for 200 electrons if I have the infrastructure. So we are the research is happening at this level. Rare earth crystal qubit. So there are plethora of qubit design. In my group, we do some research on classical computers, finding new spin-based qubit materials to look on the transition metal complexes base. So yeah, there are many different avenues of building qubits. That's again a problem, a research problem by itself. One part of the problem is optimization problem. Lowest energy means if you get to the lowest energy, you actually get the true wave function. That's the guarantee of variational principle. So if I get my true wave function psi, any other property I can measure from that wave function. If I have the wave function is like omnipotent in quantum mechanics. Only thing is that I don't know it. If I can find a way to get the wave function, and one of the ways is variational, that means lowering the energy, that wave function is true wave function. Once I get the true wave function, any other property I can get out of by measuring the expectation. The other problem that I did not discuss is how the system evolves in time. That's not a minimization problem. That's every time the time evolves the system changes its state. So that's another class of problems. So that's looks like a very nice question, but unfortunately I don't have the expertise to tell all these things. I do not know. So maybe Professor Majumdar or some other people if they know. Yeah. So it looks like it's a possibility. Yeah. No, the easy answer is why not? Especially when the logic and rhyme fails, then why not is the answer. Yeah, why not? Yes, that's the guarantee. You need to lower down the energy to get the true wave function. That's the variational principles premise. That's the premise with which variational theorem works. All right. Okay. Thank you very much. Please fill up the feedback. The certificates will be given only when the feedback form is filled.